So, dear colleagues, now we are starting with our second week, and the first lecture today will be given by Sergey Baidakov, who is an expert in gamma spectrometry and non-destructive characterizations of different materials, not only radioactive waste, but today the topic is non-destructive characterization of radioactive waste specifically. So, Sergey, please. So I will be interpreter, not the perfect one, but I will try. Sorry.
Good morning, ladies and gentlemen. I'm sorry. I will tell in Russian language. The last time when I tell in English was 4 years ago. That's why we have Vladimir Gennadievich Petrov. He is our translator. Today I try to tell you about one of method, gamma spectrometry method for the characterization radio waste. Content of my presentation. Теперь по-русски. Я хочу сказать, что я не докладываю им эти вещи не как преподаватель, а как человек, который определенное количество лет этим занимался, и вот то, что меня беспокоит, с чем я столкнулся, я бы хотел им рассказать.
So today I'm talking not as a teacher, but as a man who, or as a specialist who did all this investigation through the years, from the practical side. And today I would like to show you some points that were important for me through the years and that I faced through the years.
Yes. Content of my presentation. Non-destructive control methods, neutron activation analysis, passive analysis, gamma radiation detection mechanism for high purity germanium detectors, uniform distribution of activity in the container. It's a main question for this measure. Absorption of gamma radiation in the walls of a container. Self-absorption of gamma radiation in the sample material, matrix material, and self-absorption accounting. And I try to tell you about calibration, these systems, calibration efficiency energy, Monte Carlo method for big containers. I will tell about radionuclide library and other questions, если мы успеем. Так, первая тема. Measurement of radionuclide composition and activity of gamma-emitting radionuclides. This picture shows зависимость, dependence, the number of radionuclides of half-life, these radionuclides. Now, more than 2,700 radionuclides are now known. Stable, only 266. The rest are radioactive. About 200 radionuclides are used in various fields in human activity. Поэтому речь идет о довольно большом количестве радионуклидов, которые имеют значительный период полураспада.
That's why we are speaking about the great number of radionuclides with rather long half-life.
И если вы занимаетесь измерением радиоактивных отходов на ваших предприятиях,
so if you measure the radioactive waste in your facilities,
это превращается в нетривиальную и сложную задачу.
It can be a non-trivial and very complex task.
Вот. Учитывая, что простых схем распада радионуклидов очень мало,
taking into account that the simple schemes of the decay of gamma decay, very small number,
вы всегда будете сталкиваться со сложными схемами распада и со сложными спектрами в своей практике.
You will always face the very complex schemes of the decay and in your practice.
Но эта картинка показывает нам долину стабильности.
Yeah.
Задача ее просто рассказать, что у каждого изотопа химического элемента, вы это знаете, существуют радиоактивные изотопы, и многие из них долгоживущие.
So it's just the nuclide map that probably most of you know, and it's just a representation that every element in the periodic table has radioactive isotopes.
Да, начиная с водорода и заканчивая агонесоном.
Starting since with hydrogen and finally the last element at the moment, organison.
Типичная схема распада нуклидов, с которыми вы будете встречаться, представлена на этом рисунке. Вы видите, что здесь довольно значительное количество линий.
The typical decay scheme that you can face in your practice is represented here, and you can see that there are plenty of different lines in these schemes.
Существуют специальные ресурсы, к которым вы можете обратиться. В основном это ENSDF форматы файлов международные, где вы можете найти всю эту информацию.
There are specialized databases online available where you can find all this information.
Тем не менее, многие разработчики пишут собственное программное обеспечение для того, чтобы максимально упростить измерительные задачи, которые у вас возникают.
Anyway, many developers they build their own softwares and databases to simplify the analysis of the gamma spectra.
В частности, они стараются сделать построение радионуклидных библиотек максимально удобным для вас.
Particularly, they try to make the radionuclide databases very simple for the users.
Так, вот в ENSDF формате, например, на сайте лаборатории Анри Беккереля международной, та информация, которая вам нужна как спектрометристам, представлена в виде табличных значений и в виде графических значений.
It's just an example of ENSDF format of the Henri Becquerel laboratory, where the information about the decay scheme, about the representation of different gamma lines, are shown in a very convenient view.
Так как спектры, с которыми вы будете встречаться в своей работе, если вы будете этим заниматься, сложны, то вы должны понимать, к какому первоисточнику вы можете обратиться для того, чтобы найти эти ядерные данные, и главное, чтобы эти были актуальные ядерные данные.
So as far as you will analyze the gamma lines in your practice, you will need to find the source, the initial source of the data about the decay scheme. So you will need all the references that must be up to date.
Вот. Так, this slide shows typical spectre for high purity germanium detector. И я хочу обратить внимание на сочетание вида этого спектра, thank you, Владимир, с теми данными, которые вы видели на предыдущей картинке. Так, тут есть кнопочка, где...
Да-да-да, посерединке.
Ага.
So, and I would like to... Что ты хотел показать? Связь.
Я хотел показать связь ядерных данных в виде табличных значений.
So, I would like to show the relationship between the data in the table format with the gamma spectrum.
Да. Поэтому вы можете видеть сочетание этой таблицы
So we can see this table
и аппаратурного спектра, который вы наблюдаете, измеряя какой-то объект.
and the spectrum of your object.
This line, this line, this line, these lines. и другие. То есть для измерения содержания радионуклидов в ваших образцах вам потребуется составление радионуклидной библиотеки.
So to measure the content of the radionuclide in your samples, you will need to build a database for your experiments.
Да. К сожалению, эта библиотека не может включать большое количество линий, более чем, может быть, 100 или на 150. Это является пределом самого метода, пределом разрешения этих систем.
Unfortunately, this database cannot include more than 100-150 lines due to the restrictions of the method of the energy resolution of the devices, of the detectors.
К тому же, измеряя большие объекты, вы будете иметь дело с измененными, деформированными спектрами, где часть линий будет вообще отсутствовать.
And especially if you will measure the objects with high activity, the spectrum will be transformed, they will be modified, and some of the lines will be missed.
Так, ну и теперь два слова скажем о самом методе, что он может применяться не только для измерения радиоактивных отходов и вообще радиоактивности, но и для измерения стабильных нуклидов.
Now a couple of words of about the method itself, and just a reminder that this method can be used not only for measurement of radioactive samples, but also to measure the stable elements.
Да. It's named neutron activation analysis. Measurement of gamma radiation include radioactivity, measurement of prompt gamma radiation. Этот метод определения состава вещества, основанный на активации атомных ядер. То есть это ядерные реакции.
So this method for determining the composition of the substance is based on the activation, means on nuclear reactions.
Мы воздействуем на среду потоком нейтронного излучения, в результате которого проявляются две реакции.
We irradiate our substance with the neutron flux, and as a result, there can be two main reactions.
Эта картинка должна помочь нам понять происходящие процессы.
This picture must help us to understand the process.
Поток воздействует на ядра стабильных элементов.
So neutron flux affects the nuclei of the stable element.
Захватывая нейтрон,
Neutron is captured.
ядро превращается в составное ядро
Now there is
и
a
находится в
compound
возбужденном
nucleus
состоянии.
that is in excited state.
Это возбужденное состояние снимается спусканием высокоэнергетического мгновенного кванта.
This excited state goes to the ground state by emission of the prompt gamma rays.
Энергия этих квантов простирается вплоть до 20 МЭФ.
And energy of this gamma quanta can be up to 20 megaelectron volts.
Далее ядро, как правило, превращается в нуклид, способный к радиоактивности, то есть в нейтронно-избыточный бета-излучающий радионуклид.
Then this compound can go through the decay, mainly through the beta minus decay.
Вот. И в результате своего распада мы можем регистрировать уже излучение, гамма-излучение, которое содержится в справочниках.
And a result of this decay, we can measure the gamma radiation from the specific decay, that we can further see the energy of this gamma quanta in the databases and analyze the radionuclide content.
Как правило, это короткоживущие радионуклиды, и мы имеем большой поток гамма-квантов сразу.
Usually, they are short-lived radionuclides, and we can measure high flux of the gamma radiation.
Предел обнаружения этого метода.
Detection limits of these methods.
This table show detection limits. Для некоторых химических элементов, подчеркну, стабильных, они начинаются от 1 пикограмма.
For some stable elements, it started from 1 picogram.
Да. И для каких-то элементов это уже довольно значительные веса, 10 в 7 пикограмм.
And for some other elements, it's 10 to 7 picograms or even more.
Э, Вот. Это что касается метода измерения, применения гамма-спектрометрического метода при измерении концентрации стабильных химических элементов.
So it's about the measurements of the gamma lines when we measure the stable elements.
Более привычная для нас среда работы – это, и, собственно, тема нашей лекции – это характеризация измерения радиоактивных отходов.
More typical for us is to measure the and to characterize the radioactive wastes
Да, с применением ОЧГ-детекторов.
with the use of high purity germanium detectors.
У них был практикум какой-то?
Такого не было.
Ага. Ну, в общем, типовая схема этой установки спектрометрической представлена на этом рисунке.
So there is a typical scheme of this device, of the gamma spectrometer.
Да. Если они захотят, кто-то может зайти в комнату, посмотреть на эту систему, как она выглядит.
Yeah, if you would like, you can see the high purity germanium detectors in the, I would say, clean lab.
Посмотреть, как это работает.
Yeah, how it works.
В любом случае, есть основная система блока детектирования,
So there is a main system for the detection
в которой находится кристалл из особо чистого германия.
where the high purity germanium crystal is placed.
Он работает исключительно при криогенных температурах, примерно от минус 150 градусов и ниже.
It works only at very low temperatures from minus 150 Celsius degrees and lower.
Под воздействием гамма-излучения в этом кристалле происходит образование зарядов, которые потом снимаются электронными схемами и преобразуются в сигнал.
Due to the action of the gamma quanta, there is a formation of the charges inside the crystal that further measured and detected by other systems of the device.
Изначально короткие импульсы, которые снимаются с самого кристалла, преобразуются в линии, которые мы видим в аппаратурном спектре.
Initially, the first pulses that arise in the crystal, they are now detected as discrete lines of the spectrum.
Поэтому аппаратурный спектр, формирование аппаратурного спектра – это все, что может сделать измерительная установка.
So that's why the formation of the apparatus spectrum is the only thing that can detector make.
Поэтому, и это проблема, все остальные преобразования вы будете делать самостоятельно с помощью специализированного программного обеспечения.
All the other transformations of the spectrum you will do by with the use of the specialized software.
Автоматических систем идентификации, работающих устойчиво, нормально, на сегодняшний день не существует. Это всегда будет задачей и уровнем вашей компетенции.
Automatic systems for the analysis of the spectrum, they are not exist, and all the interpretations they so you will be responsible for the correct interpretation of the spectrum.
При этом, при работе с большими объектами, а радиоактивные отходы – это всегда большие объекты, возникает ряд специфических эффектов, которые не возникают в лабораторной практике.
And when during the measurement of the large object, the prolonged object, there are some specific effects that usually in lab practice are not occur.
Вот. И сложность и, собственно, суть этих вопросов мы будем с вами рассматривать в презентации дальше.
So, and the complexity of these questions, of these effects, we will see during this lecture.
Вот еще один слайд, который, собственно, демонстрирует соотношение и преобразование входных импульсов с детектора, где, собственно, заканчивается вся ядерная физика, и превращение их в аппаратурный спектр.
Yeah, so this is another slide to represent how the initial pulses in the detector they are converted to the apparatus spectrum. So in the detector, it is the finish of all the nuclear reactions, so nuclear processes, and then the multi-channel analyzer and all other electronics convert these initial pulses to the spectrum.
Прошу обратить внимание на один момент, что входные сигналы, выходные из детектора, это очень маленькие по величине в милливольтах сигналы.
Please take into account that these initial pulses they're very small in the value of the voltages, so it's a few millivolts.
Поэтому эти системы невероятно чувствительны к окружающим низкочастотным и высокочастотным шумам.
So that's why these systems are extremely sensitive to all the noises around the electronic device.
Обычно мобильные установки паспортизации имеют собственное питание, не связанное с сетью.
Usually, the mobile devices for the passportization characterization of radioactive waste they have their own independent source of the energy, electricity.
Так, следующий момент. Собственно, образование сигнала.
So, how the signal is formed?
Существует по меньшей мере две компоненты аппаратурного спектра. Полезная и паразитная.
There are at least two main components in the spectrum: the useful one and non-useful one, parasitic.
За образование пиков полного поглощения в спектре отвечают два эффекта.
The two effects are responsible for the formation of the complete absorption peaks energy, complete absorption of energy peaks.
Это фотоэффект и эффект образования пар.
Photoelectric effect and the pair formation effect.
И паразитный эффект, который формирует непрерывную подложку, которую мы никак не измеряем и которая нам всегда мешает, за это отвечает Камптон-эффект.
And the parasitic effect that responsible for the formation of the prolonged, it's not the noise, it's this pedestal that we called Compton pedestal. So the main effect is Compton scattering.
Поэтому в современных системах основным параметром, обозначающим качество спектрометра помимо разрешения, является вот это соотношение пик-Камптон.
So that's why in modern systems that show you the quality of the detector, it's not only the energy resolution, but also this parameter peak to Compton ratio.
Да, это как раз соотношение образования сигнала по Камптону по отношению образования фотопиков.
So it's the ratio between the intensity of the Compton signal and the peak signal.
За это отвечает частота кристалла при его росте, при его производстве на фабрике.
The purity of this crystal is the main factor that responsible for the good quality of this peak to Compton ratio.
Собственно, поэтому он называется high purity germanium.
That's why it is high purity germanium detector.
Так, для сравнения, вам эта картинка хорошо известна. Тем
Just
не
to
менее,
compare different detectors, this picture maybe a lot of you know already.
здесь представлены три типа широко использующихся кристаллов в практике.
There are three main types of the detectors.
При этом спектр набран от одного и того же источника.
And it is the same source that was measured by these three types of the detectors.
Так как вы занимаетесь радиоактивными отходами или будете заниматься и будете сталкиваться со сложными спектрами, вы видите, что решить эту задачу может исключительно только ОЧГ-детектор, в отличие от неохлаждаемых систем на органических инсталляторах, в которых разрешение просто не позволит это сделать.
As far as you are dealing with the characterization of the radioactive waste, you can clearly see that this task can be solved only with the use of the high purity germanium detectors and not with the detectors based on inorganic crystals like sodium iodide and lanthanum bromide, where the resolution is not so high.
При этом есть ряд простых задач, которые решаются этими блоками детектирования на вот этих механизмах.
But still, there are a list of the tasks that can be solved with the use of these scintillator detectors.
Далее. Несколько слов о разнице в понятиях терминологии спектров.
Just few words about the definitions and the difference in terms of different spectrums.
В результате радиоактивного распада происходит эмиссия нескольких видов излучений.
So as a result of the nuclear decay, there are emission of different types of radiation.
В зависимости от типа распада это поток корпускулярных частиц, альфа или бета частиц, а также гамма-кванты и рентгеновские кванты.
Depending on the type of the decay, there can be the release of the particles like alpha or beta particles, or electromagnetic radiation like X-ray or gamma quanta.
Поэтому суммарный спектр, nuclear emission, это, собственно, термин, который обозначает, сколько видов излучения и как количественно он испускает при радиоактивном распаде.
So that's why this nuclide emission spectrum means the total emission of all the components, all the types of the radiation due to the decay of this specific nuclide.
При этом при измерении реальных объектов мы имеем дело с спектром излучения источника.
But when we measure the real samples, we are talking about the radiation spectrum of a source.
И этот спектр будет существенно отличаться от общего спектра.
And this type of spectrum will be significantly different from the nuclide emission spectrum.
Вот. Там, очевидно, будут отсутствовать корпускулярное излучение альфа или бета.
So
И останется только гамма-излучение в основном.
Definitely we will miss the released particles like alpha or beta radiation, and we will see only gamma quanta.
Собственно, вот эта разница между теоретическими знаниями нашими об типе распада радионуклида конкретном и то, что мы в реальности будем видеть.
So it's the main difference about our knowledge about the properties of the radionuclide and what we actually we will see on the spectrum.
Из хорошего.
Good news.
Это дискретная структура спектров. Она позволяет работать с очень сложными спектрами при использовании германиевого детектора.
It is a discrete structure of the spectra that will allow us to identify radionuclides in a very complex composition.
Далее особенности этого метода – это проникающая способность гамма-излучения.
Then high penetrating power of gamma radiation.
В зависимости от жесткости излучения, от энергии излучения, мы можем видеть просматривать этот образец на значительную глубину.
Depending on the energy of the gamma quanta, we can see the source, so we can analyze the radionuclides at different depths of the object.
Далее. Наверное, 95 и более процентов радионуклидов в результате своего распада испускают гамма-излучение.
Around 95 or so percent of the radionuclides, due to their decay, normal decay, alpha or beta decay, they also emit gamma radiation.
Это позволяет довольно широко использовать этот метод при паспортизации радиоактивных отходов.
This allows to use this method of gamma spectrometry to characterize a wide range of the radioactive waste.
И что хорошо, особенно для отходов, этот метод измерения является неразрушающим. Нам не нужно готовить каким-то образом образец для того, чтобы его померить.
And what is especially good for radioactive waste, especially with high activity, that we can do this gamma spectrometry without any destruction, degradation, or decomposition of the of our sample. It is a non-destructive method, so we can measure the sample as it is.
На этом хорошее закончилось.
So it is all for the good news.
Начинаются проблемы, которые мы будем сейчас обсуждать.
And now the problems.
Первая проблема, с которой сталкивается человек, который занимается измерением больших объектов, это знание или незнание о неравномерности распределения активности в матрице этого объекта.
So the first problem that specialist faces when working with the real samples of radioactive waste, it is knowledge or lack of knowledge about the even or uneven distribution of the activity.
Плюс к обычной неравномерности распределения активности в практике встречается наличие так называемых горячих частиц.
In addition to even distribution of the radionuclides in practice, we can also meet so-called hot particles.
Поэтому перед, собственно, измерением какого-то образца с помощью гамма-спектрометра всегда предваряется дозиметрическим обследованием этот объект.
So that's why before the measurement with the gamma spectrometer, every of the objects they must be controlled with the conventional dosimetry survey to see the uneven distribution of the activity.
Критерии однородности распределения активности во всех странах разные. У нас это 30%, не превышение 30% по мощности дозы.
Criteria for even for the analysis of the even distribution of radionuclides depends on the country. In Russia, it is a deviation not more than 30% during the dosimetry survey.
В любом случае, это будет указано в ваших нормативных документах и методиках, утвержденных на предприятии.
Anyway, you will see this number, these rules in your documents, in your official documents, regulatory documents, or in the instructions at your facility.
Идеально равномерно распределенной активности в моей практике не было никогда, поэтому вопрос об этом не стоит. Вопрос стоит всегда о мере неравномерности.
I never met the ideally even distributed radionuclide in my practice.
Это связано с тем, что предприятия, которые образуют радиоактивные отходы и компактируют их, никогда не ставят себе задачи упростить ваши измерения.
It is because that when facility produce the radioactive waste, compacted it, treat the radioactive waste, there is no task for them to make it evenly distributed.
К сожалению.
Unfortunately.
Да. Поэтому нам в первую очередь нужно каким-то образом бороться с неравномерностью. И, собственно, основной рабочий метод, который применяется для этого, это вращение образца во время измерений.
That's why, first of all, we need to work with this uneven distribution radionuclide, and the first and main method to solve this problem is the rotation of the container during the measurement.
Мало того, что объект вращается, очень часто в современных системах блок детектирования поднимается вверх и вниз по вращению, проходя послойно эту структуру.
It is not only the rotation of the container during the measurement, but also elevation of this container up and down during the measurement to get the full picture of the distribution of the radionuclide.
Это позволяет свести к минимуму влияние неравномерности на измерение и получать адекватный представительный результат.
It allows to minimize the effect of the uneven distribution of radiant light and to obtain the most correct result.
Э, Эта практика имеет отношение только к объектам, имеющим ось вращения, то есть симметричным.
So it's related only to symmetrical objects.
Да. Часто в нашей практике используются прямоугольные контейнеры, кубические, прямоугольные. Там подход применяется другой.
Sometimes we see the cubic containers, and then there is another approach.
Эти контейнеры измеряются с разных сторон, на разных высотах. К сожалению, это сильно увеличивает время измерений, потому что нужно получить спектр с каждой стороны.
So these containers, they are measured from every side at different heights, and that's why the time for measurement now is significantly increasing. So it's a disadvantage of these containers.
Вот. Поэтому первичное компактирование радиоактивных отходов всегда делается в 200-литровые бочки. И они уже потом расставляются вот в эти большие контейнеры, как правило.
So that's why the primary characterization of the radioactive waste is made in these 200-liter cylindric barrels, and then after characterization, these barrels are placed in these cubic containers.
Так, это что касается неравномерности распределения активности.
So it was about the uneven distribution of activity.
Далее, второй момент важный.
The second moment.
Main question. Поглощение гамма-излучения в стенках контейнера.
The absorption of gamma radiation in the walls of the container.
Контейнеров существует великое множество.
There are a wide variety of containers.
В каждой стране действуют собственные стандарты.
In every
на
country, there
изготовление.
are specific standards for the production of the containers.
Поэтому в вашем распоряжении, уверен, будут документы о тех контейнерах, в которые будут расфасованы радиоактивные отходы.
That's why most probably you will have an information about the specific containers where the radioactive waste are placed in your case.
Это исключительно важно, потому что без знания о толщинах поглощающих сред этих контейнеров вы, собственно, никогда не выйдете на реальное значение активности в нем.
It is very important because without knowledge about the thickness and material of the walls, it will be impossible for you to correctly calculate the activity of the radiant lights inside the container.
И если толщина стенки контейнера бочки начинается от 1,5–2 миллиметров,
and if the thickness of the barrel is started from 1.5–2 millimeters,
то толщина некоторых железобетонных контейнеров может достигать 15 и даже 20 сантиметров.
So the thickness of some containers can reach up to 15 or even 20 centimeters.
Поэтому незнание этих параметров приведет к гигантскому разносу, разбросу значений измеренной активности.
That's why lack of knowledge about the properties of the containers will result in very large uncertainty and errors during the calculation of the activity.
Для некоторых нуклидов это будет порядки в 1000 раз можно ошибиться.
For some radiant lights, it can be orders of magnitudes, thousands times uncertainties.
И категория, например, из низкоактивных радиоактивных отходов перейдет неправомерно в среднеактивное значение. Это будет скандал.
And the type of the or class of radioactive waste can be transformed from the low-level waste to the intermediate-level waste, and it can be a very serious problem for the facility, can be some sort of scandal, etc.
Перед началом измерений эти данные о строении контейнера вносятся в программу как обязательные данные, даже с указанием неопределенности этих величин.
Before the measurement, all this data about the properties and construction details of the container must be placed, must be inputted in the software for the calculation of the activity, even if there is a range of these parameters.
И неопределенность знания этих величин входит в общий бюджет измерения.
And uncertainty in the knowledge of these parameters of the containers, they are inserted in the budget of the measurement, uncertainty of measurement.
Поэтому всегда для меня большой проблемой были старые, образованные еще в Советском Союзе отходы, которые нам привозили, которые не имели вот этих паспортов. Поэтому их приходилось сканировать рентгеновским сканером и определять параметры самостоятельно вот таким сложным способом.
So for me, there were quite very often problems with the very old radioactive waste that were accumulated in Soviet time, and that very often didn't have any documentation about the containers. So the first measurement of these containers was the X-ray tomography to understand the construction of the containers.
Еще раз повторюсь, лучше, не страшно, что без знания четких параметров вашего контейнера выйти на реальное значение активности невозможно.
Once again, without the detailed information about the construction of the container, it is impossible to correctly calculate the activity of the radionuclides inside the container.
Так. Эффективность есть такая характеристика, как эффективность поглощения.
And there
Она
is another
называется.
characteristic that is called absorption efficiency.
Вот. Она описывает влияние вообще всех промежуточных материалов.
It describes the absorption of all the intermediate materials.
Поэтому поглощение в стенках происходит не только самого контейнера с радиоактивными отходами,
That's why the absorption of the gamma radiation is not only in the walls of the container,
но также в конструкционных элементах самого блока детектирования.
but also in structural materials of the detection device itself.
А их существует много типов, и толщины поглощающих слоев сильно разнятся.
So there is a wide variety of the detectors. So that means that the thicknesses of the structural materials and the properties of these materials also vary.
Поэтому у вас всегда будет паспорт с характеристикой в разрезе вашего блока детектирования с указанием всех поглощающих слоев. Это сделано специально.
That's why you will always have this passport of the detection system with the construction details, with all the thicknesses of your structural materials in the detection device.
Эти данные точно так же вносятся в программное обеспечение и используются при расчете активности.
This data also is inputted in the software for the calculation of the activity and they are used for calculation of the activity.
Так, ну тут несколько слов об термине таком, как эффективность образца,
Few words about the term sample efficiency,
которая с точки зрения физики уже описывает реальный спектр и поглощение.
that is from the point of view of physics, describe the self-absorption of the sample, the absorption of the gamma radiation by the sample itself.
Да. По сути, это доля испущенных гамма-квантов, которые реально покидают материал образца.
Actually, just a fraction of the gamma ray that are released from the sample.
We don't have more time for discuss this math. Вы потом можете это посмотреть.
Yeah, we can say it. You can see it later.
Теперь как это выглядит на спектрах?
Just few examples how it looks on spectra.
На этих двух спектрах представлен источник радия-226.
On both of these spectra, you can see the spectra of the same source of radium-226.
На верхнем аппаратурном спектре этот источник измеряется без контейнера, а внизу в контейнере с 3-сантиметровой стенкой из свинца.
So on the top it is source without the container, and in the bottom it is spectrum of the source in the container, and the container is made of lead with the thickness 3 centimeter.
Помимо прочих, зеленым отмечены линии самого радия и его дочерних элементов, как на верхнем, так и на нижнем спектрах.
So with the green color, the gamma lines of radium and its daughter product are represented, are marked.
И мы видим разницу, что та низкоэнергетическая часть спектра, которая была хорошо видна, и эти линии с существенным квантовым выходом,
So you can see that for low energy gamma lines, gamma quanta, that were quite easily seen in the top spectrum with high yield.
на нижнем спектре отфильтровывается всего лишь толщиной стенки в 3 сантиметра полностью.
So they are absent in the bottom spectrum after due to the absorption by the complete absorption by this just 3 centimeter of lead.
Поэтому, немного забегая вперед, мы говорим о том, что радионуклидные библиотеки для лабораторных измерений и для измерений больших объектов будут сильно различаться.
Just saying in advance, we can say that the spectrum that are measured in the lab practice and in radioactive waste characterization for big objects, this spectra will be different.
При этом заранее знать, каково будет поглощение в стенке, невероятно тяжело, и это сложный математический аппарат. Я всегда сначала снимал первоначальный спектр и потом уже оценивал, начиная с какой области я буду работать.
So, and to know in advance what will be the absorption in the walls of the container is extremely difficult task. So, in my practice, I started to measure the let's say standard source and then estimate from which thickness of the container I will have problems.
Хочу подчеркнуть, что это измерялся точечный источник, который был помещен в контейнер. Это не распределенный объект.
I would like to notice that it was a point source of radiation, not a big object.
В нашей практике, ну, по крайней мере, в нашей, радиоактивными отходами считаются не только массивные объекты сами по себе, но и отработавшие свой срок источники, которые точно так же захораниваются в контейнерах.
In our practice, radioactive waste, they are not only bulky, massive objects, but also disused, sealed sources of radiation.
Ну и для примера еще один нуклид, гольмий 166.
Another example of holmium 166 metastable.
Здесь вы точно так же можете видеть размеченные зеленым линии.
Here you also can see this green marked lines.
И мы видим, что наиболее сильные с точки зрения квантового выхода линии, которые обычно используются, полностью пропали в контейнере.
And you can see that the most intensive lines that can be used for the analysis, for the detection of holmium, they are absent due to the absorption in the container walls.
Очевидно, граница, начиная с которой будут полностью отфильтровывать линии, будет зависеть всегда от толщины контейнера, и она будет перемещаться по спектру.
So, of course, the thickness of the container, uh, when we still can see the lines, will depend on the energy of gamma quantum and the properties of the gamma emission and the material of the container, of course.
Это что касалось поглощения стенки контейнера.
So it was about the absorption in the walls of the container.
Третий вопрос.
The third question, the third main question.
Это самопоглощение гамма-излучения в самом материале уже отходов.
So it's self-absorption of gamma radiation in the matrix, in the sample itself.
Здесь четко нужно понимать разницу между поглощением в стенке контейнера, и это характеристика контейнера, и поглощением в матрице, это характеристика матрицы.
So we should certainly understand the difference between the absorption in the container walls and it is properties of the container, and in the sample, and it is the property of the material of the radioactive waste itself.
Это наиболее, наверное, в моей практике был сложный вопрос, потому что если на контейнеры у вас всегда будут документы, то на матрицу не будет практически никогда и ничего или очень общие слова.
So in my practice, it was the most difficult question for the measurement of the activity, because if the containers, there is some certain details about the construction of the containers, you may have this information, but there is a very short or maybe a lack of the information about the properties of the material of the radioactive waste itself.
Поэтому в вашей практике это будет, наверное, основной проблемой.
So it could be the main problem in your practice as well.
В целом, самопоглощение зависит от, в основном, трех моментов.
So self-absorption depends on three main points.
Материала счетного образца,
Material
материала
of the
матрицы,
sample,
объема и формы,
the volume and shape,
и положение и ориентация этого контейнера относительно блока детектирования.
and position and orientation of this counted sample relative to the detecting unit.
Влияние на результат измерения активности самопоглощения может быть даже более значительным, чем поглощение в стенке контейнера.
The effect of the self-absorption of gamma radiation in the material can be even more important than the absorption in the walls of the container.
Поэтому специализированное программное обеспечение содержит базу данных материалов.
That's why the specialized softwares, they also contain the databases about the attenuation coefficient in the materials.
А также содержит механизм создания новых материалов из готовых составов или элементов отдельно.
And also contain the mechanism for the constructing of the new materials depending on the elemental composition.
Вот, что позволяет вам с заданной степенью точности, с заданной степенью знания этого материала ввести эти данные при измерении. И это важно.
That allows you, with the knowledge about the properties of the material, to include this information in the software for the correct calculation of the activity.
Эта формула показывает, собственно, суть линейного коэффициента ослабления и его расчета для разных материалов.
This equation represents how the attenuation coefficient can be calculated depending on the composition of the material.
Группу этих коэффициентов и их композиции использует программное обеспечение при коррекции самопоглощения.
So the software uses this number of the coefficients to correct the calculation of the activity in the material.
Хочу обратить внимание на одну величину. Это сечение фотоэффекта.
I would like to point out the specific coefficient in this equation that is cross-section of the photoelectric effect.
Сечение фотоэффекта зависит от порядкового номера элемента в степени от 4 до 5.
The cross-section of the photoelectric effect depends on the number of the elements in the 4 or 5 order of magnitude.
Поэтому для тяжелых элементов самопоглощение может быть очень значительным, невероятно большим.
That's why for heavy elements, the value of the self-absorption can be extremely high.
Те, кто будут заниматься измерением урана или плутония, отходов из урана и плутония, это представляет огромную трудность.
Those of you who will measure content of uranium or plutonium in radioactive waste, you will see this problem in your practice.
Это пример линейного коэффициента поглощения, который существует в специализированных программах, и его графическое представление для разных химических элементов: уран, плутоний, алюминий, железо.
It is an example of the linear mass attenuation coefficient that you can find in different databases, and here is the graphical representation of this attenuation coefficients for different materials, from the hydrogen to uranium and even plutonium.
И на этой диаграмме можно увидеть, как хорошо вам известны механизмы взаимодействия гамма-излучения с веществом. Сори, Владимир.
So on this graph, you can see the known for you mechanism for interaction of gamma radiation with matter,
Влияет на вид вот этого линейного
and
коэффициента.
how this mechanism the influence on the dependence of this attenuation.
В области энергии там до 500 КФ доминирует фотоэффект.
In the range up to 500 kiloelectron volts, the main effect is photoelectric effect.
В средней области энергии до 3 МЭФ доминирует Камптон-эффект.
In the range of middle energies up to 3 megaelectron volts, it is a Compton effect.
И для больших значений энергии уже доминирует эффект образования пар.
And for high energies, the main effect is the electron-positron pair production.
Да. Но основную долю поглощения вносит, конечно, фотоэффект.
But the main fraction in this coefficient have the photoelectric effect anyway.
Так, это хорошо известная вам формула, которую, собственно, использует программное обеспечение, закон ослабления узкого пучка гамма-излучения.
It is a well-known dependence of the attenuation of the gamma radiation, the exponential decrease of the attenuation, and the softwares they use this equation. So, and this equation is true for narrow beam of gamma radiation.
Это всегда экспоненциальная зависимость.
So it is always exponential dependence.
В показателе степени E всегда будет линейный или массовый коэффициент поглощения.
So here it is always a linear mass attenuation coefficient, mu,
И толщина самого материала.
and the thickness of the material itself.
В реальных матрицах материал никогда не будет представлен каким-то одним веществом.
In real samples, the matrix is not represented by only one compound.
Поэтому линейный коэффициент здесь всегда будет превращаться в массовый коэффициент поглощения.
That's why the linear attenuation coefficient is always represented as a mass attenuation coefficient.
Представляющий из себя уже групповую функцию.
That is a group or summarized coefficient.
Причем материалы с большим атомным номером будут вносить больший вклад в самопоглощение.
And of course, the materials with the higher atomic numbers will influence mostly in this coefficient.
Именно поэтому на стадии создания материала для ваших измерений и внесения его в программу стоит обращать самое пристальное большое внимание на тяжелые элементы. Нужно каким-то образом получить эти данные.
That's why in the beginning, when you construct the composition of the material in the software, you should pay big attention to these heavy elements precisely.
Наибольшую сложность представляет измерение отходов, содержащие уран.
The most difficult for the measurement are the radioactive waste containing uranium.
Потому что в процессе измерения мы сталкиваемся, сейчас скажу сначала, с обратной задачей. С одной стороны, нам нужно указать в программе матрицу, чтобы измерить уран. А с другой стороны, чтобы правильно указать матрицу, нам нужно знать количество этого урана заранее. И это взаимоисключающие понятия.
Because from one point we need to build the correct composition of the matrix, and so we need to input the mass of uranium inside of in the radioactive waste. From another side, we have to measure the content of uranium to say what is the amount of uranium in the container. So it's two tasks that depend on each other.
Вот, поэтому разное программное обеспечение применяют методы оценки равности измерения активности по разным линиям в конце.
So that's why different softwares they use the method for the estimation of the activity based on the intensities of the lines at the very end of the calculations.
И если мы неправильно внесли матрицу, у нас будет всегда экспоненциальная зависимость либо вверх, либо вниз, в зависимости от линии урана. А они 63 кева, 92, 185, 203. У нас всегда есть несколько линий для измерения урана.
These results they will always depend on the intensity of the uranium lines that actually low energy lines 63 and other kilo electron volts, and we will see how this activities they are changing with the different composition of the matrix depending on the uranium content, and they different in exponentially, either in the higher values or to the lower values.
И эта проблема, она на самом деле охватывает все измерения. Если вы измеряете правильно, значение активности по любой линии одного и того же радионуклида должна быть одинаковой в пределе ошибки.
So it is true for all the measurement of all the radionuclides. So you can be sure that you calculate correctly the activity of your radionuclide if the activity that is calculated from the different lines of your radionuclides, the values of this activity are the same in the range of uncertainty. Then you calculate the activity correctly.
Если значения активности в низкоэнергетической области отличаются от средней и высокой, значит вы что-то внесли неправильно. Либо толщина стенки контейнера, либо неправильно указана матрица материала. И только эти обстоятельства.
If the activity of your radionuclide that is calculated based on the low energy gamma lines is different from the activity calculated from the middle and high energy gamma lines for the same radionuclide, that means that something was inserted wrong in the model, either the properties of the walls of the container or the composition or properties of the matrix of the radioactive waste. And they are two main problems that can be in the calculation, two main points.
У нас это имеет ошибки при измерениях, при паспортизации у нас имеют громадное значение, сейчас скажу, потому что отходы могут попасть в разные категории. Из-за этого они будут размещены в совершенно разных хранилищах и, возможно, на разный срок, и это стоит огромных денег.
These errors can be extremely important for radioactive waste characterization because depending on this calculate and values that you will insert in the passport of radioactive waste, the class of radioactive waste can be different, low level or intermediate level. They can go to absolutely different storages, and the cost of this storage will be significantly different.
Поэтому это важно.
So it's very important.
Так, это мы уже сказали. Это массовый коэффициент поглощения, не будем на этом
Yeah,
останавливаться.
so it's a mass attenuation coefficient. You can see it can be a sum of other mass attenuation coefficient depending on the composition of the material.
Они же будут брать презентацию?
Yeah, so the presentation will be available, so we can go further. Mhm.
Так, но это из теории самопоглощения. Просто стоит сказать об одном термине. Средняя длина свободного пробега.
Next slide, please.
А,
So it's from the theory of the absorption of the gamma radiation or electromagnetic wave, and the specific term that is called the mean free path, that is marked with the letter L.
Это обратная величина линейному
So
коэффициенту.
it's just a reciprocal value of the attenuation coefficient.
Ей удобно описывать самопоглощение в материале, когда мы только планируем что-то измерять.
It is a convenient value to use to estimate the properties of the attenuation of the containers just before the measurement.
По сути, эта величина равна толщине поглотителя, для которой коэффициент пропускания равен 0,37.
So this value is equal to the thickness of the material for which the transmittance is equal to 0.37.
Исходя из этой формулы, мы видим, что через слой материала толщиной в 1L
So from this equation, you can see that through the layer with the thickness of 1L,
без взаимодействия пройдет менее 40% излучения.
so without interaction, there will be only less than 40% will pass through this material.
Через 5L уже только 0,7%.
Through 5L, only 0.7% of radiation will pass through the material.
Исходя из этих рассуждений, можно понять, почему объекты для паспортизации имеют приблизительно вот такие размеры.
So from these suggestions, you can see or you can guess why normally the objects for the characterization they have these sizes.
Если объект будет слишком большой, мы потеряем возможность измерить его правильно. Достоверность станет очень низкой.
If the object will be too large, that means that it will be impossible to measure correctly the activity inside the container.
Вот. Именно потому, что основная часть излучения, исходящая изнутри объекта, будет в нем же и поглощаться.
Because most part of the radiation that is released inside the material will be absorbed by the material.
К сожалению, мы встречались с попыткой, это можно говорить вообще, контрабанды,
Uh,
но я не буду где там или чего, но что бывают случаи попыток подложить то, что не должно быть видно на поверхности с целью избавиться от этого.
Sometimes we saw the cases when people try to hide something inside the container that should be not near the container walls, just to hide this some contrafacts, let's say.
Для примера, источник америция любой активности, абсолютно любой, положенный в центр 200-литровой бочки с плотной матрицей, не будет виден на поверхности никаким спектрометром никогда.
For example, any source of americium that is placed in the center of the container of quite dense material will be not measured ever.
Потому что толщина этого материала для него бесконечна по
Because
поглощению.
for the gamma quanta that are emitted by the americium, the thickness of this material is infinite, so we cannot measure the gamma radiation from the americium in this case.
Да, вот, собственно, следующий слайд и показывает, что бесконечные называют толщину слоя вещества, равную 7 длинам свободного пробега.
So the
7L.
infinite thickness is the layer of material that is equal to the 7 lengths of the free path, the 7L.
Поэтому огромную, чудовищную проблему представляет измерение низкоэнергетических радионуклидов, испускающих низкоэнергетическое излучение, в больших контейнерах.
That's why it is a very great problem to measure radionuclide that emit gamma radiation with low energy in big containers.
При подозрении на содержание ядерных материалов, а у них практически всегда низкоэнергетическое излучение, нам приходилось скрывать контейнеры и отбирать пробы для лабораторного анализа.
If there is any marks that there can be low energy gamma emitting radionuclides, in these cases we had to open the containers and took the materials for further lab characterization.
Самый простой и часто встречающийся пример – это америций-241 как маркер присутствия своего родителя плутония-41 и плутониев остальных вообще.
The simplest example is the americium-241 as a daughter radionuclide of the plutonium-241 and other plutonium isotopes.
Потому что встретиться с изотопно чистым америцием в отходах крайне маловероятно.
Because it is a very, very low probability to meet pure americium-241 in radioactive waste. Most probably it will be related to the presence of the plutonium.
Будьте бдительны.
Be careful.
Для тяжелых материалов, это что касается уже металлических соединений урана, корпусов, оболочек, бесконечная толщина может оказаться менее 1 миллиметра.
For heavy materials as uranium, the infinite thickness may be less than 1 millimeter.
Вы наверняка знаете, что многие контейнеры сделаны из объединенного урана.
Probably know that most of the containers they contain the walls of the containers contain the depleted uranium.
И наряду с тем, что он очень хорошо защищает от излучения, он и много чего скрывает.
So it can protect ourselves very good from the gamma radiation, but also uranium can hide something from the measurements.
Поэтому с контейнерами, которые изготовлены из плотных материалов с большим атомным номером, нужно всегда очень внимательно относиться.
We should always be very careful when we measure radioactive waste that are placed in the containers made of the heavy materials, including uranium, for example.
Так, ну это, собственно, графическое представление, почему нет никакого смысла делать объект измерительный очень большим.
So that is just a graphical representation of why we don't need to make a sample for the measurement very big.
Точно такие же рассуждения представлены в радиометрических методах измерения потока альфа или бета-частиц. Именно поэтому там такие тоненькие чашечки. Нет смысла их делать толще.
The same suggestions are true for the measurement of alpha or beta particles. So there is no reasons to make the counting samples very thick.
Смысл этого эффекта точно такой же.
So it's the same idea of the effect.
Вот. Ну, в этой табличке сами вы сможете посмотреть величины L, бесконечный 7L для различных материалов.
So in this table, you will be able to see by your own the different values of L and infinite thickness 7L for different materials for different energies of gamma quanta.
Вот вы видите, что для тяжелых материалов вот с такой вот
For example, for heavy
плотностью,
materials,
для низкоэнергетических это, излучателей это очень маленькие величины толщины,
for
которые
low
будут
energy
бесконечной.
gamma quanta, it is very small infinite thickness. It's 0.1 centimeters.
Например, для свинца бесконечная длина для линии 59 КЭФ всего 12 миллиметров.
So for the lead, for the energy of 59.5 kiloelectron volts, it is only 12 millimeters, the infinite thickness of absorption.
Вы можете положить источник любой активности, хоть 100 кюри, в маленький контейнер с такими, и ничего не увидите на поверхности.
So that means that you can place the source with even very high activity, up to 100 curie or even more, in the container with this just very thin walls, 12 millimeters, and you will see nothing on the spectrum.
Так, едем дальше. Несколько слов о подготовке системы, потому что это довольно непростой вопрос.
Just few words about the preparation of the system before measurement, because it's important and not a very easy question.
К сожалению, для больших объектов не существует относительного метода градуировки. Нет таких источников, их никто не продает.
Unfortunately, for massive objects, there is no standard sources for calibration.
Энергетическая градуировка позволит вам обучить ваш спектрометр правильно измерять энергию и только.
So the calibration by energy will allow your detection system to measure correctly to identify correctly the radionuclides, and this is the only thing that your detector will be able to do.
Чтобы получить реальное значение активности, нужно проводить теми или иными методами градуировку по эффективности регистрации.
To calculate correctly the activity of the radionuclide, the calibration by efficiency must be made.
Поэтому сейчас в мире используются в основном два метода: полуколичественный метод или полностью математический метод Монте-Карло.
So in the world there are two main approaches to make efficiency calibration: either semi-quantitative quantitative method or fully mathematical method.
Для реализации метода Монте-Карло нам нужна исчерпывающая информация как о строении детектора, так и о строении измеряемого объекта.
To use this mathematical method Monte Carlo, we need to have a full information about the object of the measurement and about the detection system.
Вот именно поэтому, я еще раз подчеркиваю, очень важно знать характеристики ваших контейнеров, ваших материалов и вашего детектора. Всегда держите это наготове.
So I would like to point it once again that it is very important to have the full information about the properties of your detector, about the material that you measure.
Вот, программного обеспечения довольно много разных вариантов существует. Мы работаем в программной среде LCRM, которая, в общем, сейчас доминирует на российском рынке в 95% случаев.
There are quite a lot of different softwares available for the interpretation of the gamma spectra. In our practice in Russia, we use the software called LSRM.
Оно получило широкое распространение, и мне доводилось в Италии на атомной станции Энрико Ферми ставить это программное обеспечение и работать там именно на паспортизации отходов.
It is widely used, and I even used it at Italian nuclear power plant in the lab of Enrico Fermi to characterize the radioactive waste.
Она многоязычная, любой язык вы можете выбрать.
So it is multi Linguinal.
Да. Несколько слов о блоках детектирования излучения и градуировочных источников, которые вам понадобятся на стадии энергетической градуировки. Это те, кто будет реально заниматься, если захотят, откроют презентацию и
A
посмотрят.
few words about different types of the detectors and the standard radionuclides that you can use for the calibration of these detectors.
Да. Если вы планируете решать задачу паспортизации радиоактивных отходов, вам неизбежно придется проанализировать существующие модели детекторов.
So if you will work with the characterization of radioactive waste, you will need to go through the list of the detectors that exist nowadays.
Типовых три в основном штуки. Это рентгеновский диапазон, это стандартный диапазон и широкодиапазонный.
So there are three main types of the detectors for the X-ray range of the electromagnetic waves from 3 to 300 kiloelectron volts, for the specifically gamma quanta from 40 kiloelectron volts, and for the kiloelectron volts, and the wide range of the energies, so from for the X-ray and gamma rays.
В практике паспортизации радиоактивных отходов и измерения больших объектов широкодиапазонные и низкоэнергетический рентгеновский не используются, потому что в этом нет никакого смысла.
In the practice for the characterization of radioactive waste, the broad range and the X-ray range, the types of the detectors, they are not used because there is no need to use them.
Да, потому что низкоэнергетическое излучение, менее 50 КЭФ, застревает, как правило, в любой стенке контейнера, особенно если это распределенный объект. Представительность будет крайне низкой.
Because low energy of gamma quanta, they are absorbed almost in all types of the containers and massive objects. So we will not able to measure these low energies less than 50 kiloelectron volts of gamma quantum.
Поэтому, в общем-то, в практике во всем мире я всегда встречал блоки детектирования вот с такими вот стандартными характеристиками. Могут спросить, почему 3МЭВа? Потому что в 3МЭВа укладывается, ну, наверное, 99% долгоживущих радионуклидов, с которыми вы можете встретиться.
So usually in my practice and all over the world, there is a use of this first type of the detectors with this range of energies detected up to 300 megaelectron volts, 300 megaelectron volts, because around 99% of all radionuclides that emit gamma rays lay inside this range.
Так как остается совсем мало времени, я покажу несколько слайдов по, собственно, внесению данных по созданию моделей для измерений.
Just few slides about how to insert data for the in the model for the measurement.
Вот таким образом выглядит в разрезе любой блок детектирования на основе ОЧГ.
So it is how the detector based on the high purity germanium looks like.
А вот и русский язык, который мог быть английским. Вот.
For
Просто
Russian.
обращаем внимание, что огромное количество поглощающих слоев, которые нужно обязательно учитывать, и это только для детектора.
Just take into account that there are quite a lot of different layers that we must to take into account when we model the detector, and it is only the detector part of the system.
База данных материалов связана с таблицей Менделеева, поэтому вы можете выбрать любой элемент, в том числе из которого исполнен блок детектирования. Может быть, карбон, бериллий, алюминий.
So there is a database of the materials that are connected also with the, of course, periodic table of elements. So there is already a list of the parameters for these materials, and you can combine them.
Да, ну и, собственно, создание модели Монте-Карло вашего объекта.
So and it is the Monte Carlo modeling of your object.
И расчет вот этой функции отклика то есть эффективности для конкретного вот этого объекта, который вы потом будете пользоваться, если он типовой.
And the calculation of the efficiency of the measurement for your specific object.
Так, ну и два слова про радионуклидные библиотеки.
So, and just a couple of words about the radionuclide libraries.
Радионуклидов много, схема распада у них очень сложная. Поэтому создать единую библиотеку на все случаи невозможно.
So there are a lot of different radionuclides with quite a complex decay scheme. So it's impossible to build the universal database.
В методических материалах очень редко встречаются какие-то разделы по методологии создания радионуклидных библиотек.
In different methodics, it is not written how to build about the methodology, how to build these radionuclide libraries and databases.
Поэтому это всегда будет результатом вашей подготовки, вашего мастерства. К сожалению, здесь очень дорого можно ошибиться.
That's why it is, unfortunately, it is always the question of your expertise, how to build correctly these libraries.
Именно поэтому в нашей среде совершенно нормально люди пересылают друг другу спектр, задают вопросы более опытным от менее опытных. То есть вот эта вот среда, она создана, и мы общаемся с тем, чтобы правильно проводить идентификацию.
That's why it is absolutely normal to communicate between the experts in this field to send each other spectra, to ask questions. Did I make the calculations correctly or not? It is typical for these specialists.
Последняя фраза. Особенно это важно для измерения больших объектов, потому что в этом случае еще будут деформированы сами спектры, и вам даже стандартной библиотеки придется править.
Especially, it is important for the massive objects because the view of the spectra, they will be modified, they will be transformed due to the different effects. And that's why even in this case, the standard libraries must be corrected.
Спасибо за внимание.
So, thank you for your
1:28.
attention. Yeah, it's time for questions. If you have any questions? Yep.
Do you use a key zero method to perform absolute calibration? When you use the neutral activation and gamma spectrometry techniques?
K0 метод для абсолютной калибровки. Не знаю, что это. Для нейтронно-активационного анализа и гамма-спектрометрии. Can you say some words about this K0 method? Yeah.
And the nuclear reactor too.
Может быть, MCNP имеется в виду какая-то оболочка, расчет эффективности по потокам излучений. Но, скажем так, вот Монте-Карло, который включен в наши программы, это по сути часть MCNP. Просто в обрезанном виде.
MP method. So the Monte Carlo method is part of this method, but not the.
Okay.
Yeah.
Okay.
Yeah.
To determine a radio 226 is a bit difficult because uranium 235 is an interference.
Радий 226 трудно определять, может быть, потому что уран-235 накладываются линии. Как быть?
Во-первых, у урана-235 помимо основной линии 185-78 есть еще три: 143, 163 и 204.
So, uranium-235 has also other lines. Какие еще раз?
143,
143,
163, 204.
163 and 204.
У них квантовый выход меньше, но они прекрасно проявляются в спектре.
They have a lower quantum yield, but they still can be seen in the spectrum.
Помимо этого, в равновесии с радием находится свинец-214 и висмут-214, у которых десятки линий, в том числе в высокоэнергетической области.
And normally there is equilibrium of radium to 6 and lead to 114 and bismuth. So that also have different lines and we can use them for measurement of radium.
А равновесие между ними наступает меньше, чем сутки.
So equilibrium between radium and lead is in less than 1 day. So it's easy to use these lead lines and bismuth lines for the calculation of radium as well.
Мы это так обходим.
Bismuth.
Mm-hmm.
Energy of bismuth 214.
Yeah. Mm-hmm.
Да, но действительно эти линии интерферируют, да, мы это видим, 185-78 и 102, и 186-21.
Yeah,
Да, они не разделяются даже лучшими спектрометрами, это факт.
It's true that these lines around 186 kiloelectron volts, they interfere and they cannot be the resolution of even very best detectors are not enough for the
It's a fact.
separation. Yeah. Thank you. Any more questions? If not, then thank our speaker again. Спасибо, Сергей.
Thank you for your attention.
Now we have a small coffee break. Yeah. Я думаю, можем начать. Давайте включим. Okay, dear colleagues, and we continue with our next lecture given by Sava Savanyuk from the Pilot Demonstration Center Uranium Graphite Reactor Decommissioning. So please, the floor is yours.
Okay. Hello. So in this report, we will talk about experience in decommissioning. This report will consist of 3 different parts. First, we will talk about comprehensive engineering and radiation survey. Then we'll talk about dismantling of building structures. And finally, dismantling of nuclear fuel cycle equipment. So let's talk about comprehensive engineering and radiation survey. So this survey, as its name suggests, consists of engineering and radiation survey. We will later discuss each in detail. Conduction of this survey for decommissioning is necessary and critical information component at the final stage of life cycle of the facility. Based on the results of this comprehensive survey, the operating organization ensures the development of design documentation for decommissioning and prepares a decommissioning safety justification report, which is required to obtain a license for decommissioning of the facility. Conduction of this survey includes a set of activities aimed at obtaining information on the engineering and technical condition of buildings, structures, systems, and equipment, as well as on the radiation situation in the premises and on the nuclear plant site, including information on volume and surface contamination with radioactive substances, and qualitative and quantitative composition of radioactive waste. This survey is performed to assess the actual technical and radiation status of systems, equipment, buildings, structures, utilities, and the territory of the facility site, as well as the volume and aggregate state of accumulated operational radioactive waste affecting the safety of personnel, population, and environment. This comprehensive survey is conducted to develop and submit to the regulatory authorities the necessary documentation for obtaining a decommissioning license, such as the survey results report, decommissioning program, decommissioning design documentation, safety justification report, and others. The scope and tasks of this survey depend on the decommissioning strategy being implemented. Based on the decommissioning option adopted, for example, in the immediate dismantling strategy, the role of radiation survey will be greater. And in the delayed dismantling strategy, the role of engineering survey will be greater. It can be concluded that a comprehensive engineering and radiation survey is the information base for selecting a specific decommissioning option, as well as for developing decommissioning design documentation and safety justification report. Sources of information for organization, preparation, and conduction of this survey are design documentation, operation history, technical condition data, and annual status reports. In order to justify the choice of methods and scopes of the survey, facilities are usually categorized by functional purpose, by provision of decommissioning works, by safety class, and by conditions of location in different radiation exposure and control zones. A general program is developed for the comprehensive survey. This program contains a description of the forms of conducting different types of survey, composition of preparatory works, and measures for their implementation. The objectives for developing the overall comprehensive engineering and radiation survey program are determining the timing of the list of activities, defining a list of organizational and other documentation, including measures to ensure the safety of personnel involved in comprehensive survey work scope, and determining the materials and equipment that are needed to carry out the work,
Special working groups are created when organizing the work. They may include representatives of relevant organizations and enterprises, as well as specialists of the operating organization. So let's talk about comprehensive engineering survey. The main objective of the engineering survey is to assess the technical condition of systems, equipment, building, and metal structures. At the stage of preliminary, that is visual inspection, the categories of technical condition of the constructions, depending on the existing defects and damages, should be established by external science. So it may be a normal or good condition, which implies that there are no visible damages or cracks evidencing decreasing load-bearing capacity of structures. Satisfactory condition, which implies minor damages are present in some areas, and unsatisfactory condition, where there are damages, defects, cracks, evidence and limited good working order are present. And finally, emergency condition means that existing damages evidence that structures are unfit for operation and pose a collapse threat. During the preliminary inspection of load-bearing structures, special attention should be paid to columns, crane beams, trusses, and load-bearing elements. Based on the preliminary inspection, a work program for detailed survey should be drawn up. Detailed, that is, instrument-aided survey, is carried out to obtain initial data for verification calculations. Results of comprehensive engineering survey are as follows. So the end result should consist in assessment of technical condition and residual life of buildings and constructions, and assessment of technical conditions of physical barriers preventing the spread of radioactive substances. So let's talk about methods and methods of conducting an instrument-aided engineering survey. These methods include destructive methods and non-destructive methods. Destructive methods of quality control of concrete and reinforced concrete structures include shear test method and method of statistical control of concrete strength and homogeneity. The most used non-destructive methods are ultrasonic inspection and acoustic emission methods. The other type of survey is comprehensive radiation survey. The main objective of the radiation survey is to obtain representative information on the radiation characteristics of systems, equipment, building concrete and metal structures that have been exposed or have been in contact with radioactive media, namely to study the radiation situation in the premises, to determine the activation level of the equipment, to determine the levels and composition of surface contamination with radionuclides of building structures, rooms, systems, equipment site, to determine radionuclide concentration and composition, and finally to assess radionuclide concentration and composition in the air of working premises. The end result of comprehensive radiation survey should be a data set allowing to assess radiation status and level of radioactive contamination of the territory, activation level and radionuclide composition, mass and characteristics of radioactive deposits within systems, equipment and pipelines, scope, aggregate state, and classification of radioactive waste accumulated during operation and generated during decommissioning. So let's talk about techniques, methods, and tools of comprehensive radiation survey. Information on radiation situation of the territory, system structures, groundwater, and soil should be obtained using approved and certified techniques on the basis of analysis of several factors. Some of them are gamma radiation fields, measurements performed after the final shutdown, results of surveys, including direct and indirect measurements performed after the final shutdown. Also, direct management data obtained by collecting samples, such samples as soil, groundwater, concrete, paintwork, etc., and the examinations under laboratory conditions. and also calculated data obtained using computational methods to assess the radiation status and radioactivity accumulated in systems, equipment, building, and protective structures. When conducting a comprehensive radiation survey for decommissioning, the following techniques are used. Measurements of spatial distributions of gamma radiation dose rate, management of beta and alpha particle flux density on the surface of contaminated equipment and building structures, collections of samples and preparations of samples and their measurement, collection of samples by wiping, cold cutting to isolate a fragment of material, and also electromechanical reaction and coring. And finally, determination of radionuclide composition and specific activity of gamma radiation sources. The used methods should be all certified. So there are three types of measurements taken. There are gamma radiation dose rate measurements, determinations of loose surface contamination, and spectrometric survey. Gamma radiation dose rate measurements are those measurements that can be carried out using dosimeters and radiometers at a distance of 0.1 meters for maximum gamma radiation dose rate, or at a distance of 1 meter for average background gamma radiation dose rate. No, this is on the same slide. Yes, the same slide. And also, measurements of gamma radiation dose rates can be carried out using dosimeters at a distance of 2 meters for minimum value of gamma radiation dose rate. Determination of loose surface contamination as the third type of measurements taken is the determination of non-fixed loose beta and alpha contamination on the surface of structures, such as walls, floors, and it is carried out by wiping methods and by sampling. After taking a sample from material, load activity is measured based on which the contamination level of the controlled surface is calculated in surface activity units. And finally, a spectrometric survey is a determination of specific activity of radionuclides in samples by gamma spectrometry methods. So let's talk about current trends in comprehensive engineering and radiation survey field. Traditionally, all measurements and results of the engineering and radiation surveys are performed manually. With mapping of the facility radiation situations, this huge amount of data, the manual processing, huge areas of surveyed premises, leads to data simplifications, as workers are not able to physically combine the received radiation data with information on the actual condition of the structure and equipment. Therefore, only implementation of digital survey allows for an extremely accurate digital perception of the facility and its parameters. Laser 3D scanning and panoramic photography are used instead of the usual manual labor. Digital survey is the process of obtaining data on the engineering and radiation status of the facility in which the actual and archived data collected are in digital format and systemized structure. This means that the collected data are purposefully grouped around a pre-prepared framework, a three-dimensional information model of the facility, that is, of the nuclear and radiation hazardous facility. As a result, the information model obtained as a result of a digital survey becomes the basis for digital decommissioning design. So the next topic is dismantling of building structures. This report will contain only practical aspects. Using the example of two completed projects, we will look at the features and peculiarities of the dismantling. Dismantling refers to the main stage of the decommissioning project. As a rule, it is performed after the release of the object from systems and equipment placed in it, and also after decontamination and obtaining a report on the radiation safety of building structures. Let's consider different approaches to dismantling on example of two finished projects. The first one is decommissioning of buildings 804 and 802 at Engarsk Electrochemical Combine. So this is it on the left here. And the second finished project that we will talk about is decommissioning of U5 installation at High-Tech Research Institute of Inorganic Materials in Moscow. Buildings 804 and 802 are one story with a basement. In terms of plan, the building is rectangular in shape with overall dimensions of 67 meters wide and 964 meters long. Height is 70 meters, basement floor height is 2.7 meters. There are 10 ventilation chambers that are attached to the building along the longitudinal walls. The building is divided by transverse expansion joints into 19 blocks. The sequence of works for liquidation of the building include conduction of visual inspection that will help for development of measurements for instrumental inspection of building structures. Then conduction of instrumental inspection of building structures. Then strengthening of building structures with indication of the conditions for the safe performance of dismantling works. Then will be mechanical decontamination, such as abrasive or chipping decontamination of building structures. And finally, dismantling of building structures. Also, we transfer metal structures not contaminated with radionuclides to the operating organization for sale. Then comes processing of reinforced concrete building structures not contaminated with radionuclides at the crushing and sorting complex. And finally, formation of secondary crushed stone for subsequent backfilling of excavation pit. So the excavation pit is where there was a foundation of the building. So to fill up this pit, we use material not contaminated with radionuclides. So let me go back. On this slide, we can see dismantling was carried out in 3 stages. So it was carried out sequentially for each 1/3 of the building. The building was divided by 3 parts, as it's shown on this slide. So there were certain types of work carried out, such as removal of the roof, dismantling of floor slabs, dismantling of external internal walls, dismantling of metal trusses and columns, and finally dismantling of floor covering. In accordance with the adopted design decisions, the foundation of the building were not removed. At the transition to the next stage, a tent shelter was installed along the entire height from the side of the demolished part of the building to prevent the possible release of radionuclides along with construction dust. So what are features that can be distinguished here? So there are 3 main features due to the fact that according to the results of the survey, the building was in a particularly emergency condition. For the safe performance of work, it was necessary to strengthen building structures, which required significant time and financial costs. The second feature is that the dismantling of the building was carried out in stages. That is, after the dismantling of equipment and systems in 1/3 of the building, this part of the building was cut off and it was demolished, dismantled, This made it possible to simultaneously carry out various works. While one third of the building is being demolished, equipment is being dismantled in another part of it. And the third feature is that construction waste not contaminated with radionuclides was processed at the sorting and crushing complex and used for backfilling of the excavation pit. The second project is decommissioning of U5 installation. Works on the liquidation of the building of U5 unit at Moscow High-Tech Research Institute of Inorganic Materials were carried out in a completely different way. The building of the U5 installation was put into operation in 1945. The building was a 4-story, intended for industrial experimental work using various nuclear materials, radioactive substances, and sources of ionizing radiation. The building is located on the industrial site of Moscow High-Tech Research Institute of Inorganic Materials. Based on the results of the radiation examination of the U5 facility, it was found that indoor pollution is caused by and local sources of beta and gamma radiation with a dose rate of up to 150 millisievert per hour. In accordance with the design documentation, a decision was made to decommission the U5 unit under the liquidation option. The territory of the installation is surrounded on all sides by dense residential development. Radioactive substances which are present in significant amounts in accumulated radioactive waste, premises, equipment, and special communications pose a potential hazard to personnel, the public, and the environment. In the premises of the installation, there was a complex of equipment that ensured the functioning of the U5 installation, on which studies were carried out to develop the technological process for the separation and purification of plutonium from fission fragments from uranium irradiated in nuclear reactors. The first semi-industrial batches of plutonium-239 were obtained at this facility, and the industrial technology was developed. The installation was mothballed in 1965. Subsequently, part of the equipment was used to collect, store, and extract plutonium from liquid radioactive waste. As a result of the operation of U5, a number of technological premises and equipment were heavily polluted and were mothballed during the reconstruction of the building in the late 60s. Part of the premises of the former U5 was used as a laboratory for working with radioactive substances of the first and second class of radiation hazard. The building contains 2 shafts with extraction columns and 2 sets of premises with hot cells. By the time the work began, most of the premises were contaminated with radioactive substances of various physical and chemical composition. Part of the premises is dilapidated, communications are corroded, the condition of the building of the U5 installation can be assessed as unsatisfactory. Works were carried out in 3 steps. As you can see on this slide, there are 3 steps. So the first is creation of the necessary infrastructure, dismantling of the main technological equipment, dismantling of communications and engineering objects. The second step is removal of radioactive waste from building structures, decontamination of building structures, making a report on the radiation state of building structures of the U5 facility. And the final step is dismantling of building structures, including foundations, and also rehabilitation of the territory, obtaining a report on the radiation state of the site. Also, on each stage, there was radioactive waste management carried out as radioactive waste was generated at each stage. During the work, the following deviations from the design solutions were identified. After the decontamination of building structures, studies were carried out and an expert opinion was obtained indicating the presence of multiple local radiation anomalies on the first and basement floors of the U5 facility. At the same time, the continuation of decontamination work was impossible due to the risk of violation of the bearing capacity and collapse of the building structures of the installation. Due to the presence of contamination of building structures that exceeded sanitary standards, the dismantling of the first floor and the basement of the U5 facility, according to the design solutions, posed a risk of spreading radioactive substances into the environment, especially taking into account the location of the object in the center of residential development in the city of Moscow. To ensure safety during disassembly and during dismantling of the installation, it was proposed to perform a number of compensatory engineering and technical measures not provided for by the project. It was decided to carry out dismantling works in 2 stages. The first stage was dismantling of roof, 4th, 3rd, 2nd floors, up to the overlap of the 1st floor, creation of protective shelter equipped with engineering systems. On the 1st floor, the systems included ventilation, radiation control, etc. And the 2nd stage was to dismantle the remaining building structures. Thus, it is proposed to use the structure of the 1st floor as an additional safety barrier for the further work of decontamination of building structures and removal of radiation-contaminated soils by isolating it and equipping it with ventilation, dust suppression, and radiation control systems. At the same time, to perform dismantling work inside the protective shelter, it was proposed to use small-sized, remote-controlled dismantling machines. A technical solution was prepared for the dismantling of the unit, and a corresponding project for the production of the works was developed. The decommissioning project was completed on time, safely, and with proper quality. So what are features that can be distinguished here? So there are 3 features. The first is inability to fully complete decontamination work due to the risk of collapse of building structures. Second is the need to design an additional safety barrier for dismantling. And the third feature is that dismantling work was carried out in cramped conditions using small-sized remote robotic tools. So let's talk about dismantling of nuclear fuel cycle equipment. So I will give you general information on dismantling of nuclear fuel cycle equipment. That is ED, or equipment dismantling. ED refers to the main phase of the decommissioning. The works carried out in the framework of ED included disassembly of large equipment, fragmentation of equipment elements, and sorting by contamination level and morphological composition, and etc. So what is to be dismantled? It is main process equipment, auxiliary equipment, and process networks, also utility systems. This subject, this report will only be about dismantling of main process equipment. So methods used during this equipment dismantling are classic methods, which include oxy-fuel gas cutting, plasma arc cutting, rope source, etc. And also new promising method which is laser cutting. Limitations on the use of particular ED method are economic feasibility and impact on personnel and operating conditions such as fire hazards, tight working space, types of contamination, and also type of ventilation used. We have a completed project on equipment dismantling. It is a decommissioning of nuclear fuel cycle equipment as part of decommissioning of building 804 at Angarsk Electrochemical Combine. So in 2020, the project for decommissioning of the uranium isotope separation workshop that is building 804 was completed at Angarsk electrochemical combined site. General information about the project. So the building 804 is part of the nuclear installation for uranium hexafluoride production with uranium-235 nuclide enrichment up to 5 weight%. Concerning a decommissioning option, the liquidation option was adopted, including complete dismantling and liquidation of the process systems, of utility networks, communications, as well as building structures of building 804. Also, rehabilitation of the territory. Dimensions of the building are 67 meters wide and about a kilometer long. And also 65,000 meters of built-up space, and there are 10 one-story vent extensions adjacent to the buildings. Specialists of the operating organization carried out comprehensive engineering and radiation survey of this building, and the results of which became the initial data for the development of the design documentation. Work stages included preparatory works, which is creation of necessary infrastructure, physical protection system, radioactive waste recycling area, waste accumulation and management areas. The next stage of work was engineering and radiation survey of building structures. Then dismantling of utility equipment and networks. The next stage was dismantling and disassembly of the diffusion systems and interblock pipe communications. Then dismantling of building structures. Management of waste generated. And finally, bringing the territory into a radiation-safe condition. That is a rehabilitation of territory, backfilling of the excavation pit with inert material, and sowing of lawn grasses. In 2020, the work scope envisaged by the project was fully implemented. Here you can see the main numerical indicators of the completed project. As you can see, the project is large scale. Let me remind you that uranium isotope separation workshop that is building 804 is about 1 kilometer long. Nevertheless, the main stage was implemented in less than 4 years. Over 5 specialized organizations were involved in the course of work. So we can see these numerical indicators. Concerning dismantling of process equipment, quick facts and figures. So there are 15 blocks of diffusion machines subject to dismantling in building 804. 330 machines in total. Total weight of metal structures is 5,000 tons. The machines in building 802 and 804 were arranged in blocks, and each block consisted of 22 machines, that is 22 units. Each unit includes a lot of assemblies. As you can see on this slide, there are process tank with filtering cell cartridge installed in it, lower compensator, upper compensator, upper and lower compressors used to cool down the working gas after its compression by the compressors. Also pipe assemblies, valves for splitting into separate volumes, etc. That is a lot of assemblies just in just one unit. To prepare the equipment for decommissioning, the following work was performed to prepare it for dismantling. So it was necessary to flush the equipment internal cavities with air-ammonia mixture to remove non-volatile deposits of uranium hexafluoride from the equipment internal cavities as much as possible. Also pumping out gaseous treatment products, that is air ammonia mixture from equipment, and purging in internal cavities of equipment with air. Also, it was necessary to remove power supply to the motors and disconnect power supply cables. Then it was needed to disconnect and remove instrumentation and automatic equipment. Also, it was necessary to drain water from the unit equipment cooling system. And finally, to purge the unit's cooling system with compressed air to remove residual cooling water. So this all are just preparation for dismantling. The actual dismantling of gas diffusion equipment was carried out in top-to-bottom sequence. Main methods of dismantling are plasma cutting and hand cutting tools. Radionuclide contaminated assemblies were placed in intermediate sites separately, according to the results of the preliminary categorization and the intended recycling methods. All dismantled assemblies were craned to a special site, to a special intermediate storage area lined with polyethylene film to prevent contamination of the area due to falling of process deposits from the internal surfaces of the equipment. So concerning plasma cutting as chosen method for equipment dismantling, why plasma? The technology of plasma cutting of metals is based on creating an effect by means of an electrical discharge in gaseous medium, and is suitable for processing metals up to 50 millimeters thick. Plasma, the closest competitor to plasma is oxy-fuel cutting. Oxy-fuel cutting of metals, and it does indeed offer good results. However, plasma systems are considered to be more versatile, high-speed, and high-quality cutting methods. Cuts made with plasma cutter always have less draws, less bending, and smaller hard area. The small width of the cut using this technology is provided due to the high concentration of energy in the cut zone. Plasma cutting is by far one of the most cost-effective methods of thermal cutting. The advantage of plasma cutting is achieved by eliminating the need to regulate the gas supply and control the chemical reaction of combustion. The plasma metal cutting machine is designed for contact cutting of sheets. So when using it, it is not necessary to make efforts to maintain the distance between the torch and the workpiece. Plasma technology can be used to cut any metal that conducts a current, including mild steel, that is low carbon steel. Also aluminum, stainless steel, copper, and most other types of metal. Unlike plasma, oxy-fuel cutting involves a chemical reaction between oxygen and iron, so it is only used on low carbon steel. At the moment, the decommission of building 802, a complete analog of building 804, is in process. About 50% of the work envisaged by the design documentation has been completed already. The building was freed from equipment. Also, building structures are already decontaminated. Some part of the building was dismantled, and solid radioactive waste generated during the decommissioning, as it is brought to the acceptance criteria, is compacted into safe containers and transferred for final disposal. The decommissioning of building A2 is planned to be completed in this year, in 2025. A complex for management of metal waste contaminated with radionuclide substances has been created at the work site. All generated waste is recycled. The following technologies for handling metal waste contaminated with radioactive substances are used. So we use fragmentation workshop with special equipment that allows cutting large diameter pipes. We also use abrasive blasting machine, which decontaminates fragments of equipment by removing a layer of oxides and material from the surface. We also use liquid decontamination, during which parts of metal equipment are placed in a special solution for a certain period of time. Cryoblasting is also used. So it is analog of sandblasting, but in this case, dry ice under pressure is used instead of sand. And we also use pyrometallurgical processing to produce ingots. In contrast to decommissioning of building 804, this project started using a mobile laser complex. During the testing fragmentation of diffusion machines, this complex was put to the test. So it should be noted that at the moment, testing is still in progress. So there are advantages of laser cutting. It allows fragmentation and dismantling of gas diffusion machines at a considerable distance. It also allows dismantling in cramped conditions, and it makes it possible to fragment these machines without disassembly and without extraction of filter elements. The results of testing confirmed that the stated technical characteristics. You can see some of them are that maximum power output is 20 kilowatt. Also, optimum cutting speed is about 3 millimeter per minute. That is at a metal thickness of 220 millimeters. So the final provisions are as follows. Methods of equipment dismantling may differ. Methods are evolving. It all depends on the cost, operating conditions, and safety. So that is all. Thank you for your attention.
Thank you. Thank you for your presentation. I have a question. What kind of waste minimization techniques do you use? And what kind of declassification techniques? What I mean is high-level waste to low-level waste have been used before in your projects. Thank you.
Concerning high-level waste, we just, I suppose, we place it in a facility, in storage facility to bring it to medium level waste, and then we hand it over usually to the operator, which has experience in dealing with this kind of waste. So, and concerning other type of waste, that is low level waste. We have some methods to recycle it, such as if it is graphite waste, we have a installation for burning it to reduce volume and also to reduce some of this activity. There are also other methods of waste management, but I don't have enough information about it.
So, thank you for your presentation. My question is regarding the rhodium fluoride, which you mentioned that you flushed it and washed it with air ammonia mixture.
Yes.
So what happened after that for the residual rhodium fluoride? You washed it to where? Didn't you store it to somewhere? Became a mixture of air ammonia plus rhodium fluoride and any contamination level also with that?
Mm-hmm. I don't think I have information on that. What they did after they flushed it with air ammonia, perhaps they have handed it over to the organization that manages waste, because I don't think we have experience in waste management of such class.
So I guess it was collected also after the process.
Yes, maybe.
With respect to the operation. Thank you. Hello again. I have another question. What was the difficult part for you in such those dismantling projects? There were different types, like it could be a fuel cycle facility decommissioning project, it could be reactor decommissioning, it's all different.
The difficult part, the most difficult part.
Yeah, the cutting techniques, or it's more about your concern is more about those rates for workers, or main concern, what's the stressful part? What will be the challenging, let's say, challenging part in your opinion?
Challenging part, in my opinion, I think the challenging part is to choose the decommissioning option.
Decision?
To choose the decommissioning option. So there are usually two decommissioning options, which is liquidation option or another option of decommissioning, which implies that the facility is decommissioned on site, that is buried on site. All its radioactive waste is stored on site. So this is, I think, the main challenge when concerning decommission is to choose the strategy, because you have to you have to always be a forerunner and to foresee how you will implement your developed technologies for decommissioning, because it never has any standard procedures when it comes to individual facility. There are many types of decommissioning ways, of decommissioning methods. So we even have developed a specific equipment that are not found anywhere, just to decommission certain projects. So as you can imagine, it is very creative work, and I guess it is the most hard part of it.
It's more operational, as I understand. Okay, thank you.
So yes, the next lecture will be soon. Thank you.
Since the discovery of X-rays, radioactivity, and then the use of nuclear energy, one of the most important areas of joint activity of scientists and practitioners has been ensuring the safety of people and the environment. This area of work still remains a priority. And then choosing the parameters of new nuclear technologies, it is decisive. The modern world cannot be imagined without nuclear energy. The use of radioactive isotopes and radiation in medicine, geology, industry, and many other practical areas. Today, nuclear energy provides over 14% of global electricity production and about 17% in Russia. The plans for its development that have been formed and have begun to be implemented in recent years, including in Russia, allow us to talk about the renaissance of the nuclear energy. Providing obvious environmental advantages in comparison with fossil fuel energy, peaceful nuclear energy, however, often meets with a negative attitude from society. This is due to, firstly, the fairly close associative and, in some countries, including Russia, technological relationship with nuclear weapons. Secondly, with issues of ensuring the safe operation of nuclear power plants and caution regarding the impact of radiation on humans and the environment. Thirdly, with the final stages of a nuclear fuel cycle, handling spent nuclear fuel, radioactive waste, and decommissioning of nuclear power facilities. Due to historical particularities, for many decades, our country lacked the practice of solving problematic issues in the field of nuclear energy industry, and to the greatest extent in the field of spent nuclear fuel and radioactive waste management and decommissioning. The result of such practice was the systematic accumulation of radioactive waste, spent nuclear fuel, and stopped nuclear power facilities that had no clear prospects for their evolution, the so-called nuclear legacy problems. These problems became a kind of payment for the implementation of nuclear defense program for an extremely wide front of scientific research in the field of reactor physics and the nuclear fuel cycle. The solution of nuclear legacy problems related to the handling of spent nuclear fuel and radioactive waste, as well as the decommissioning of nuclear power facilities, is currently of a strategic importance for ensuring the nuclear and radiation safety of Russian Federation. Now I would like to tell you a little about the history of establishment and the development of an enterprise where I work. Since the early 1950s, radioactive substances in our country have become increasingly used in science, industry, and medicine. In this regard, there was an urgent need to create centers to ensure the collection and reliable long-term storage of radioactive waste. By a decree of USSR government in 1956, a decision was made to design and build 35 regional centers on the territory of the Soviet Union to organize the collection, transportation, processing, and storage of radioactive waste. Such centers were later called the radon specialized plants. 16 radon plants were located in Russia, 6 in Ukraine, and 1 in each of Union Republic. The Moscow specialized plant built 17 kilometers from the city of Sergiev Posad in the Moscow region was considered the leading organization in the network of centers for the handling of radioactive waste. The site for the construction of a Moscow radon was chosen, taking into account geological features and clay soils that prevent the migration of radionuclides into the environment. In 1958, a project was approved for the construction of radioactive waste disposal station. On February 2, 1960, the Council of Ministers of USSR decided to establish the radioactive waste disposal station. At that time, due to the strict secrecy, the enterprise was given a name Postbox 662. In September 1980, the Council of Ministers of USSR decided to establish a radioactive waste disposal station. Ой, так, это уже был. In September 1980, the administrative, engineering, technical and working personnel of the enterprise necessary for the implementation of its production activities were fully formed. In connection with this, the management team collectively decided to time the date of a celebration of radon anniversary to the end of this important process. Since then, the enterprise has celebrated its anniversary every third Friday in September. September 19 will mark the 65th anniversary of Radon Enterprise. The first trip of 8 special vehicles for radioactive waste took place on January 27 in 1961. The waste was collected from 2 sites, the Kurchatov Institute and the Shukinskaya water treatment plant. Moscow radon served as a kind of experimental site where technologies for handling radioactive waste were developed and implemented, and specialists in the nuclear industry were trained. In 1963, a method for the combined disposal of liquid and solid radioactive waste in a cement concrete monolith was put into operation. In 1968, the enterprise was named the Central Radiation Safety Station, and the main technological complex was put into operation at the industrial site of an enterprise, which later housed installation for combustion, pressing, concentrating, and vitrifying radioactive waste, as well as a number of laboratories. In 1980, the enterprise was renamed the Moscow Scientific and Production Association Radon. In 1986, radon specialists were among the first to participate in the assessment and the liquidation of the consequences of a disaster at the Chernobyl nuclear power plant. In 2001, the organization was renamed the State Unitary Enterprise of Moscow, United Ecological, Technological and Scientific Research Center for Radioactive Waste Neutralization and Environmental Protection. In 2008, 15 regional special plants of a radon network became part of the Rosatom State Corporation as the departments and branches of the formed structure FSUE Rosrao. But the Moscow radon is stayed out of the structure. In 2013, the organization was renamed the Federal State Unitary Enterprise of Moscow, United Ecological, Technological and Scientific Research Center for Radioactive Waste Neutralization and Environmental Protection, and became part of Rosatom State Corporation, but remains outside the structure of FSUE Rosrao. In 2018, FSUE Radon was appointed as specialized industry operator for the management of nuclear legacy sites. Based on the order of State Corporation Rosatom, facilities within the industrial site of JSC Vnicht, located at the edges Moscow Kashirskaya Шоссе building 53, were transferred to the economic management of FSUE Radon. The Moscow branch of FSU Radon was established on the basis of the industrial site of JSC Vnicht. In 2020, FSUE Rosrao was renamed to FSUE FIO. In accordance with the order of the State Corporation Rosatom dated 2022, the transfer of facilities intended for the storage of radioactive waste from FSU FIO to the economic management of FSU Radon has begun. Thus, in 2024, all former Radon special plants located in the territory of Russian Federation, as well as former branches of FSU FIO Northwest Center Sevrao and Forest Center Dalrao, become part of the FSU Radon. In essence, all production sites of these branches are nuclear legacy objects. Currently, FSU Radon includes 11 branches located throughout Russia, from Kola Peninsula to Kamchatka. In this slide, you can see the 11 branches and 22 industrial sites of FSU Radon. The majority of nuclear legacy facilities were created in 1950s, 70s. At that time, the design and documentation for nuclear facilities did not consider decommission issues. Since this was not included in the list of mandatory requirements for nuclear and radiation safety. These facilities are currently located in 40 constituent entities of Russian Federation. The ultimate goal of FSUE Radon as an industry operator for the management of nuclear legacy facilities is to decommission such facilities and return land, building and structures to the national economy. Decommissioning of nuclear facilities is a relatively new area of activity, the relevance of which is already high and will increase over the next decades. A wide range of tasks solved during decommissioning is due to its close relationship with related topics, ensuring nuclear and radiation safety, handling radioactive waste and spent nuclear fuel rehabilitation contaminated areas, as well as political and socio-economical aspects. Decommissioning of nuclear facility in accordance with the national regulatory documents is an activity carried out after the termination of operation of nuclear facility, excluding its use for its intended purposes until complete of partial release from radiation control by state safety regulatory bodies for the use of nuclear energy. The process of decommissioning of nuclear facility can be divided into 3 stages. The first stage, preparation for decommissioning, which includes the following activities: removal of spent nuclear fuel, nuclear materials, radioactive waste, radioactive process media from equipment systems, premises, radioactive waste storage facilities, conducting a comprehensive engineering and radiation survey, development of design documentation for the selected option for decommission a nuclear facility, taking into account the results of comprehensive engineering and radiation survey, development of documentation to ensure the safety of decommissioning, obtaining a license for decommissioning and others. The main stage the performance of decommissioning that includes following activities: decontamination, dismantling of contaminated equipment, building structures, premises, buildings, processing, conditioning and transportation of radioactive waste generated during decommissioning for disposal, rehabilitation of a contaminated area, and the final stage of decommissioning, which includes performing a control radiation survey, obtaining a sanitary and epidemiological conclusion for the rehabilitation territory, removing the nuclear facility from the control of regulatory authorities. Typical radioactive waste storage facilities built in the Soviet times, located in the industry sites of former radon plants, are near surface reinforced concrete tanks of various internal volume. An example of such typical storage facility is shown on the slide. According to the project, these storage facilities were to become final disposal sites for the radioactive waste. Waste was placed in the bulk after the filling the storage facilities. They were filled with the concrete, covered with concrete slabs, and then sealed with a band of on the roof of a storage facility. This approach to handling radioactive waste exists until the publication of a federal law on handling radioactive waste in 2011, after the adoption of which the initial registration of radioactive waste accumulated during operation was carried out, while the waste accumulated in the storage facilities was recognized as removable. The storage facilities that continued to be used to receive radioactive waste were close to these special hangars to protect them from precipitation. An example of hangar is shown on the slide. And the next video shows us the Volgograd industrial site. Короткое. Тише можно. Здесь. В принципе, можно дальше ничего не будет. Currently, the removal of accumulated radioactive waste is one of the most expensive and technically complex operations in the cycle of decommissioning radioactive waste storage facilities. This is due to the lack of development and technical solutions, accumulated experience, as well as the need for reliable justification of radiation safety during the performance of work, development and approval of documentation that complies with the current regulatory and legal acts. Currently, the following work is being carried out in the branches of and departments of FSUE Radon in preparation for decommissioning and decommissioning. As a part of execution of as a part of the execution of government contract from the 2023 to 2026, preparations are underway for decommissioning of industrial sites of Ural branch, Blagoveshchensk, Samara, and Volgograd departments. Measures have been implemented to make the necessary changes in the terms of licenses for the operation of radioactive waste storage facilities, obtain sanitary and epidemiological conclusions for the work, manufacture, supply, and install frame sand shelters to protect storage facilities from precipitation, and arrange infrastructure to support decommissioning work. Currently, accumulated radioactive waste is being removed from the storage facilities, further conditioned and transported to disposal. In Grimiha department of the school center, Sevrao, as part of preparation for decommissioning work is underway to remove spent nuclear fuel and radioactive waste from the territory of the sites. In 2024, under the government contract, the Grimiha department disassembled, containerized, and sent the last spent removal part of a reactor with liquid metal coolant to FCUE Mayak for reprocessing. Now all the spent nuclear fuel has been removed from Grimiha department, and work has begun to extract the accumulated radioactive waste from the site. In 2024, under government contract, the unloading of spent fuel assemblies from Lenin nuclear icebreaker reactor began from the Andreevo Bay storage facilities. Next video shows the process of developing and using a remotely controlled complex for removing spent fuel assemblies. Да, нормально. И получилось? Не хочет? Что не очень. Ну ладно. Даже потише. Громко. Равно громко. Да. Дальше надо прикрутить немного. Дальше прикрутить, наверное, немного, да. Ну, ладно, пусть покажет. Ну, так не да. And this is a work that was made in the storage facility. Где надо. одну засуну, там можно. Я не попал. Можно просто увеличить, стресс. Есть там такой. Было ускорить, конечно. Ладно, сейчас он засунет это. Вот. Достаточно, наверное. Ну, или что? So the damaged spent fuel assemblies was extracted from the storage facility. Now work is underway the decommission of Moscow branch. The Moscow branch is located in southeastern administrative region of Moscow, the Kashirskое шоссе 53. The next slide shows the work to bring the one of a building of Moscow branch to a radiation safe condition. The contaminated equipment was removed, the building structures were decommissioned, then the building was demolished, the contaminated soil was removed, and the pit was backfilled with clean soil. The work on decommissioning the Moscow branch is planned to be completed in 2026. Decommissioning of the Luchinsk branch first slide shows us decontamination and dismantling of the contaminated buildings structures. Then the contaminated area was rehabilitated. Contaminated soil was removed. The pit was backfilled with clean soil. The grass and shrubs were planted. The work on decommissioning the Luchinsk branch is planned to be completed in 2026. In the future, branches of FCU Radon plan to begin work on extracting accumulated radioactive waste from the storage facilities of Nizhny Novgorod, Irkutsk, and Khabarovsk departments. Also in the plans for the development of a product line of FCU radon for decommissioning as promising project, work is underway in following areas. Creation of mobile teams to perform decommissioning work which will include decommissioning specialists in all areas, creating mobile decommissioning points to enable prompt execution of work and reduce the costs of creating additional infrastructure for decommissioning. Development of decommissioning technologies, introduction of robotics, remote controlled mechanism, and new technological equipment for performing work, and the expansion of the scope of enterprise activities with release of work in the field of decommissioning of nuclear power plants and rehabilitation of contaminated areas. Currently, work on decommissioning of nuclear legacy facilities of FSUE Radon is at initial stage of formation. This is mainly due to the need for significant development of a regulatory framework, solution of technical, technological, environmental, socio-economic, and other issues for the safe performance of work, and bringing the decommissioned facilities to the state required to confirm the removal from the register by the safety regulatory authorities for the use of nuclear energy. With the accumulation of sufficient volume of practical work on decommissioning, with the solution of problematic issues of nuclear legacy, this mechanism will become more streamlined, technically and economically efficient. Thank you for your attention. Is there any questions? Thank you. I think it's all.
Но у меня нету кармана вообще. Я на стол положу. То есть я вот так.
Dear colleagues, please take your seats. We continue our school. So I'm glad to introduce Nadezhda from Rosatom, and she will tell you about the key aspects of environmental impact assessment. Please, Nadezhda, the floor is yours.
Okay, let's start. Yes. Good afternoon, dear colleagues, students, and friends. My name is Nadezhda Zdanevich. I'm head project manager of Rosatom International Network. I start with few words about myself. I'm a radioecologist. I studied nuclear physics and radiochemistry in International Sakharov Ecological University. Regarding my professional activity, I participated in development of environmental impact assessment legislation in Belarus. Since 2015 till 2020, I was member of the implementation committee of ESPA Convention. Now I'm engaged in environmental radiation safety issues. Today, I'm very briefly introduce you with history and origins of environmental impact assessment, main aspects of the ESPA Convention. We are talking about EIA stages about notification, preparation of the documentation, consultation between parties, adoption of final decision on planned activity, and post-project analysis. As you know, environmental threats and ecological consequences do not respect national borders. So environmental protection is a cross-border issue and has led to the creation of transnational regulations in that area via multilateral treaties. The United States the United Nations Conference on the Human Environmental held in Stockholm in 1972, played key role in the creation of international instruments related to the environmental protection. In 1975 was adopted final act on the Conference on Security and Cooperation in Europe. This final act, known as Helsinki Declaration. This declaration committed countries to improve their environmental conditions through collaborative efforts, scientific research, and development of healthy human environment. In the early 80s, EIA procedures were included in the legislation of many European countries. ESPA Convention was negotiated to provide an international legal framework for transboundary environmental impact assessment. And in 1997, ESPA Convention, its short naming of Convention on Environmental Impact Assessment in Transboundary Context, ESPA Convention, entered into force. ESPA Convention sets out the obligations for parties to assess the environmental impact of certain activities at an early stage of its planning. Further to ESPA Convention, each party should take necessary legal and practical measures to ensure environmental protection. On this slide, you can see parties to the convention, and for example, from I know that a participant from, for example, Belarus. Who see your country on this slide? Belarus, Kazakhstan, maybe? Hello.
So I can name all the countries which are present. Yeah.
Okay, maybe participant can see naming of.
I'm afraid that
No.
trace. Simply not.
Only Belarus party of the ESPA Convention. Yeah, it's good because Belarus has a very good experience on implementation ESPA Convention according to construction of Belarusian NPP and as a proposed activity in that countries. But I know that, for example, China, Egypt, Russia, India. No. Has a very comprehensive legislation in that area, and of course, a lot of mechanism and approaches of EIA procedure they have in legislation, environmental legislation of these countries. So any document begins from terms and its definitions. And main terms of ESPA Convention is party of origin and affected party. Party of origin means the contracting party of ESPA Convention under whose jurisdiction proposed activity is planned to take place. Affected party is the party likely to be affected by transboundary impact of proposed activity. Of course, convention gives us a definition of proposed activity. proposed activity, environmental impact assessment, and we should understand that assessment, first of all, is a national procedure for evaluating the likely impact of a proposed activity. And if during our assessment we found out that environmental of other country will be affected by our proposed activity, this national procedure will contain transboundary procedure. It's understandable. So from ESPA convention, we define main participants of EIA procedure. If you are party of origin, in this procedure will participate competent authority. I mean, for example, Ministry of Ecology, Ministry of Environmental Protection, Ministry of Energy, Ministry of Health, Ministry for situation. Да, Ministry for не так. No, okay, disaster situation. Of course, it will be a customer of proposed activity, performer of EIA work. It's different, for example, design or project institution that create project documentation for your proposed activity. Different experts in, for example, experts on impact assessment on air, water. For example, experts in seismic hazards and so on. Of course, during EIA procedure, a lot of non-governmental organizations could be involved. And of course, national public, involvement of national public is regulated by Aarhus Convention. It's another convention, another international treaty of UNEC about participation of public in ecological decision. If you present affected party, from affected party will participate in EIA procedure competent authorities, the same authorities that in party of origin, different experts, non-governmental organization, and international public. And for example, I present in this slide guide of UNEC about good practice recommendations on application of the convention to nuclear energy related activities. And here I present ссылка, Ольга. Ссылка, link to this document, and you can study it. On this slide, you can see subject of the ESPA convention. And of course, according to topic our school, first of all, we are talking about nuclear facilities, nuclear power plant, and other nuclear reactors. We are talking about installation for spent nuclear fuel management, installations for radioactive waste management, and installations for production of nuclear fuel. All project documentation on construction, on modernization, on decommissioning of these facilities is under IAEA procedure, under ESPA convention. Proposed activity listed in Appendix 1 of the ESPA convention. And when we are talking about NPP, we should understand that all reactors of a nuclear power plant, including dismantling and decommissioning, is subject of ESPA convention, except research installations. When we are talking about spent nuclear fuel management, we are talking about installations for the processing and reprocessing of spent nuclear fuel, installation for final disposal of this fuel, and for storage. On this slide, you can see main steps of the IAEA procedure. Every procedure will start from notification. Next day, notification of affected party. Then preparation of IAEA documentation. Next stage is consultation between parties. And when consultation is finished, country of origin should establish a final decision and transmit it to affected parties. And optional stage of a procedure is post-project analysis. So we will start from notification. Notification is the first step of the IAEA procedure. And if your country is a party of ESPA convention, you should notify all parties that can be affected by proposed activity. ESPA convention applies only to countries that are parties to the ESPA convention. It's a common practice, but for example, if we go to Belarusian case, Belarusian NPP, Belarus, for example, notified Russian Federation, but Russian Federation is not a party of ESPA Convention. And other side of aspects of notification, when Austria Belarus should Belarus also notified Austria because Austria was interested to participate in EIA procedure. First, that we when we are talking about notification, first of all, we should talk about timing of notification. And the ESPA convention says that notification should be as early as possible and no later than when informing its own public. In some case from Armenia, according to lifetime extension of Metsamor NPP. Armenia notify Azerbaijan about prolongation of NPP сейчас NPP уже по-русски забыла. Да. Prolongation of NPP notify Azerbaijan in 3 days after Armenia notified own public. Через 3 дня. And Azerbaijan подал жалобу. Azerbaijan claimed to implementation committee about non-compliance of Armenia regarding ESPA convention. 3 days. When we prepare notification, we should know about content of this document. Notification should correspond to the Article 3.2 of the Convention and should contain information about nature of the proposed activity, information about spatial and temporal boundaries of the proposed activity, and expected environmental impacts and proposed mitigation measures. After receiving the notification, affected parties should respond and confirm its participation or inform about non-participation in EIA procedure. In participation is and after when country of origin respond about participation in this procedure, it can request the information about environment of affected party with regard to prepare EIA documentation. This slide contains information about content of notification. And for example, notification should contain whether the activity is listed in Appendix 1 to the convention. Should contain a description of activity, scope and scale of activity, location and description of the location. Also, country of origin should include maps and other pictorial document to the notification. About expected environmental impacts and proposed mitigation measures, country of origin should include information about scope of assessment, information about expected impacts on air, water, land, and so on. And of course, information about measures to prevent, eliminate, or minimize environmental effects. When party of origin goes to next stage of preparation of the EIA documentation, it begins from scoping report. In different country, it may be a scoping report or for example, a program of EIA. It depends on national legislation. And first of all, scoping report is prepared for determine the extent of issues to be considered in final report. And of course, scoping report should be transmitted to affected parties for consultation and with public and local authority. After that, country of origin should prepare final report. It's detailed description and justification of proposed activity. The reasonable alternative should be assessed at geographical and technological alternatives. Of course, final report content very precise information about environmental impact assessment. Monitoring and management program, and of course non-technical summary, because non-technical summary is object for example, for consultations with public. When you provided EIA documentation to the affected party, consultations begin. Time frame for the duration of the consultation has to be defined by the parties. taking into account national legislation on public participation. It's very important that consultations should always be conducted before the final decision on proposed activity. Article 5 of ISSPA Convention suggests issues to be discussed during consultations. First of all, parties are discussing possible alternatives for the proposed activity, as geographical as technological. Also, monitoring issues can be discussed, and of course, mitigation measures and post-project analysis. ISSPA Convention provides different forms of the consultation. It can be official consultations at sufficiently high or medium level. Also can participate different bodies and experts of sectoral authorities. Also consultations may be provided through the joint body and electronic meetings, exchange of emails or official letters. When consultation is finished, party of origin prepare final decision. It could be decision on environmental impact prepared by Ministry of Ecology. It could be conclusion on environmental expertise. It could be decree on decree or other legislative act on construction or decommissioning of nuclear facility. It's very important that this final decision contain reasons and considerations for the affected party. And as I said earlier, post-project analysis is optional stage of EIA procedure, and decision on providing this analysis is accepted during consultations between parties. Post-project analysis is typically based on the monitoring of the activity and its impacts. PPA, when you decide to carry out PPA, country of origin should prepare a program for PPA, and according to this program, PPA will be conducted. Opportunities provided by the EIA. Of course, EIA procedure, EIA consultation gives us a basis for discussion with neighboring country, and as I say EIA procedure is one of approach of ecological diplomacy in our world, and of course EIA procedure give us transparency of information about proposed activity, about their impacts on environmental. EIA procedure can help to involve public into the ecological decisions and so on. And what will be if, for example, country of origin will not provide notification? According to the article 3.7, affected party can request to submit sufficient information for the purpose of holding discussion, and it's this article 3.7 is used for activity that is listed in Annex 1. And of course, affected party can initiate EIA procedure not only for listed object, but for the object that для которых for which Annex 3 is applicable. And for example, if country affected country miss deadline for notification, affected party can inform the implementation committee about failure of comply as per convention. So if for example, country of origin didn't request the environmental information from the affected party. Of course, documentation on EIA does not take into account characteristics of the affected environment and for example, impact standardization requirements. So could be needed a revision of the EIA documentation after consultations. And when we talking about consultation, for example, country of origin didn't все, я уже позабыла все слова, Оля. Не установила, didn't establish, for example, deadline for submitting comments. This situation can привести.
Can lead
To delays of consultations. And when you have any obligations according to ISSPA convention, and you can't to comply to ISSPA convention. This convention has compliance mechanism. Working body of ISSPA convention, such as implementation committee, verifies the compliance of the parties with their obligations in order to assist them in fulfilling their obligations. Two mechanisms of compliance control. The first one is submission of the parties, and the second one is committee initiative. Following to the submission or committee initiatives mechanism, the implementation committee drafts decision on compliance of the countries. Decision on non-compliance contains measures to be taken by the non-compliance party. Also, by meeting of the party, can be made a decision to suspend the implementation of the proposed activity in order to bring the EIA procedure into compliance with convention. And of course, this situation is very bad and may lead to increase of financial resources, increase of time and human resources, and as well as lead to image losses, decreased confidence to the project, problems with financing, and loss of competitive advantages. That's all. Thank you for your attention. And if you have any question, please.
Would you please stand up and
Sure.
and louder a little bit?
Yeah, thank you very much for the presentation. So my question is about the ESPO and the Early Notifications Convention of the IAEA. How different are they from each other? And then I think this is only for countries in Europe, European countries. So comparing it to the Early Notifications Convention, how is, for example, a state that, let's say a new state trying to build a nuclear power plant, since there's no, I don't know, kind of convention like, maybe I don't know if there is, maybe there actually exists such a convention. How is it going to be for a new member state?
As I understand, you mean a convention on early notification about nuclear accident?
Yes.
Of EIA.
Yeah.
Да. It's different international treaties, and ESPA convention is a treaty of UNEC, and convention on early notification about nuclear accident. It's about nuclear facility and treaty of IAEA. Yes. And there is different notification, because when we are talking about ESPO convention, we are talking about notification on proposed activity. And when we are talking about IAEA convention, about early notification, we are talking about nuclear facility that is under эксплуатируется, under operation. And during operation of this nuclear facility, we have some nuclear accident. Yes. And this different time of notification. Notification according to ESPO convention is да.
Как в случае новых, вы говорите, что вот тот вот тип оповещения, да,
Да.
вы говорите, он действует для европейских стран. А как это будет работать для новых стран-участниц? Для новых государств, которые будут присоединяться к IAEA, например?
Какой конвенции присоединяться?
Ага. You should clarify what convention do you mean? So you are talking about the new states, right? Correct?
Yes. So
Yes,
as I
so
understand,
they are joining to what?
for example, the question is, what's the main difference between the ESPO and the Early Notifications Convention? And I think she explained it, and I now understand. But I have a follow-up question from the explanation she gave.
Okay.
То есть я ответила, что это
Yes,
абсолютно.
yes. Okay, so for ESPO, does that mean a member state, for example, planning to, say, build a facility that's going to affect the neighbor, right? Does that mean you have to notify the convention and also the IAEA, or when you notify ESPO, it's directly linked to the IAEA? We have to do those two notifications separately.
Кого нотифицировать, кого уведомлять? Вот я не понимаю.
Whom we should notify? What is the audience for notification? Please
Okay.
clarify.
So let me use a scenario. For example, let's say Finland, right, is going to build a facility that is going to affect, I don't know, a neighbor to Finland, right? So as I understand, ESPO needs to be used, the convention, right? And I'm asking, if you notify ESPO as you apply the convention, does that mean you have to do that and also talk to the IAEA, or you don't need to do those two? Because as I know, IAEA also needs to be notified, right?
IAEA
Yes.
should be notified as an international organization?
Yes.
No. According to ESPO convention, you should notify only a neighboring country that, first of all, party of the convention. And if you want, in frame of environmental diplomacy, you may notify neighboring country that are not party of ESPO convention.
Okay. Thank you.
But if neighboring country is party of ESPO convention, you oblige to notify this country. In case of transboundary impact.
Okay, thank you.
Any other questions, please? I believe we can start. Good afternoon, colleagues. My current lecture is dedicated to the dismantling while at the decommissioning process. I will particularly stop on the questions of the remote dismantling. So during the I will talk about that in particular because remote dismantling is non-alternative modern method. My current presentation is subdivided into 4 sections. The basic approaches toward dismantling, the object for remote dismantling, cutting methods, and the technical solutions applied for remote dismantling. I will talk about the dismantling of reactor facilities. Извините, чуть помедленнее и чуть покороче фразы. Спасибо. Talking about the practical words in the course of dismantling. Those can be subdivided into 4 general directions. Upon the final shutdown of the reactor, so we are dealing with the operating of what we just have stopped. So the operation still continues. So we are dealing with the waste management as well. So we're facing with decontamination issues and dismantling issues. So dismantling is the main factor of dismantling. Planning the decommissioning. The dismantling is not considered as a part of just removal of the facilities. Dismantling is always a complex of works, including fragmentation and transportation. Depending on the type of the object we are dismantling, it includes the removing the object from the site, the fragmentation of the facilities dismantled, dismantling of the metallic constructions, dismantling of the activated facilities, dismantling of building constructions, and deconstruction of the building, demolishment of the building.
Общая схема работ по выводу из эксплуатации представлена на схеме. Это прикреплен.
This is a very general scheme of dismantling.
Готовки площадки к выводу из эксплуатации.
The first step is to prepare the site for decommissioning.
Планирование.
On this stage, we do the preliminary planning.
Чистых систем.
Then we start to dismantle the clean systems.
В машинном зале.
Everything that is in the operational side.
Здания чистые, которые.
And all the buildings, all the facilities, the clean facilities that are attached to the operational site.
Далее приступает к монтажу поверхностно загрязненного оборудования.
The next step is to dismantle the facilities decommissioned on the surface. This is the major works on the dismantling of the facilities. The next step is to dismantle the activated equipment. This is the most sophisticated and the most science-contributing part of the process. Then we have to deactivate the free spaces, the free sites. So the surface is cladding, right? The cladding is dismantled.
И, собственно, демонтируют те системы, которые обеспечивали работу по выводу из эксплуатации.
And the equipment used for the process of dismantling are also detached, dismantled. So after that, the sanitary passport is obtained for the object. And the site is totally destroyed.
На слайде представлены стандартные мероприятия, которые выполняются при дистанционном демонтаже.
Here you can see the scheme of the, как вы еще раз сказали? The standard steps taken to the dismantling process. This is a consequent scheme of operations. Some of them can be performed in parallel. So what steps are to be taken before of the dismantling process? This is the observation, pre-dismantling survey or pre-dismantling observation. So the shut off the object of dismantling from electricity, from water supply, etc. The preparation of documentation required for dismantling. The preparation of the staff structure. The organization of transportation routes.
Проверка и подтверждение работоспособности основного оборудования, обеспечивающих систем. Испытания оборудования.
The testing of the equipment needed for dismantling.
Основной блок работ связан непосредственно с демонтажом, включает в себя демонтаж оборудования со штатного места.
So the process of the very process of dismantling includes the dismantling itself.
Его временное размещение.
Its temporary storage.
Проведение необходимости дополнительных измерений.
The necessary measurements are also to be taken at this step. The passover of dismantled equipment on the stationary site of cutting. The cutting itself, the sorting out and the characterization of the pieces.
Как уже говорил, мы будем рассматривать дистанционный демонтаж на примере демонтажа реакторных конструкций.
As I've mentioned before, we will stop in particular on the reactors dismantling.
Здесь показана схема, это схема реактора ВВР-440.
Here you can see the scheme of the reactor WWER-400.
Здесь у нас в России.
So we have this type of reactor here in Russia, in Ukraine, in Eastern Europe as well, in Armenia, in Cuba.
Это реактор, аналог pressurized water reactor, ПВР.
This is the analog of pressure water reactor.
Он из себя представляет вертикальный сосуд.
This is a vertical vessel.
Еще бетонный шахтер.
So it is located in a cavity.
Корпус реактора устанавливается на кольцевой бак.
So the pressure vessel is established on the ring tank, annular water tank. So inside the reactor, you can see the inner part of the reactor. To organize the process of getting the power. All of this equipment has, so all of this equipment is contaminated with neutrons. It's activated by neutrons. On the slide, you can see the data. On the characteristics of and the activity is also represented here. The most active construction is the core basket. When the fuel sticks are placed, not stick, but cores, right? Rods, okay, rods. And this is the protecting tube zone.
Конструкция, которая сверху накрывает топливные стержни.
The construction which is covered from the top of the fuel rods
И не дает им всплыть.
And doesn't allow them to float up in the process of exploring. So this is the bottom plate, upper plate, and middle plate. And the protective tubes are going through the whole constructions from the upper, middle, and lower plates. As per activity, we see that the character of neutron activation of different plates is different. The closer we are to the fuel rods, this is the lower plate. This is the most active part of the construction. It fits the category of high activated objects, which is above the upper plate, is not activated. This is how core basket look like. So inside it, the fuel rods are placed. It's all is of highly activated. This is the inner vessel cavity. It is very highly activated in the center. In its upper part and lower part, it is these are the points of low activity. This is the bottom of the cavity. So if you know Russian matryoshka doll, all of these constructions are one in another, from the smallest to the biggest, layer by layer. Here we can see the character of the contamination. We can see that cobalt-60 prevails. It determines the dose of the contamination. These are so-called radioactive vectors of the construction for different nuclear power plants, for different NPPs. This is Slovakia, Germany, and Russia. This scheme represents the power of dose. We can see that in the center of the in the center of the construction, the dose is maximum. Once the composition of the construction, the radionuclides composition of the construction is determined, we can estimate the time for fragmentation of the construction. So by use of the handwork, in fact. So we can see now that the core basket might be cut into pieces only in 130 years approximately. While planning the dismantling works, we can first determine the sites of the work. The content and the number of the sites of work depends on the strategy of the dismantling works. We determine what should we do to dismantle to dismantle the equipment in fragments, or just a whole the entire construction is to be dismantled. In the remote dismantling, we can determine the 4 sites in general.
Непосредственно со штатного места, где расположено оборудование.
First is dismantling on the site where the facilities and equipment is situated, are located. The fragmentation zone of this equipment and facilities.
Контейнеризация фрагментов.
The containerization of the pieces and fragments. And the storage zone. I would like to underline and to stop in particular on the methods of cutting, which are implemented in case of remote dismantling. Look, the situation is like this.
Выполнить резку можно разными способами.
You can cut in many ways.
И опыт применения различных способов резки, он есть.
And there is various experience on different types of cutting.
И каждый оператор для себя решает, каким путем ему пойти в зависимости от той ситуации.
And each operator decides what method of cutting is to be taken into consideration, depending on the experience he has and depending on the features of the project he is dealing with.
Все методы резки одинаково эффективны.
Not all the ways of cutting are equally effective in case of remote cutting. There are some requirements towards the methods of cutting. In the best case, those should be applicable for underwater use. Of course, they should be reliable and safe at use. They should provide the high effectivity. And they have to have the elementary base for the use. They should minimize the generation of secondary waste and minimize radiation exposure and stuff. Of course, provide the required cut quality. And they should apply the minimal force on the proceeded surfaces. Usually, on the preparation side, we decide by what means and how we will cut the fragments of the facilities. In fact, as a rule, it is done on the basis of multifunctional analysis of the situation. By the way, a big seminar will take place in IAEA this December. Will be dedicated to the multifunctional analysis while deciding what type of cutting is to be chosen. Замечательно. Okay. The methods of multifunctional criteria while choosing the way of dismantle of highly activated facilities. Am I right? It includes determining the context for decision making, determining the list of methods, so several comparison criteria is chosen, and there should be a definition of these criteria. The qualitative criteria is done, is performed.
Присваиваются веса каждому критерию.
So each criteria has its own weight.
Это значимость.
So the weight of meaning, an abstract thing. So the quantitative evaluation of cutting methods is also to be done. And the priority is given to the method which got the highest score.
На слайде перечислены основные методы резки.
So the main methods of cutting is listed here.
Подразделяются на механические,
So they are subdivided into mechanical ones,
термические
thermal ones,
и гидрофобические.
and water jet cutting as well.
И здесь представлены критерии.
And here you can see the comparison criteria. To solve the task which is listed here, in fact, we are looking through all of these methods for our obstacles, for our conditions. Either we see the single method or integrity of methods.
Вообще дистанционная резка может выполняться на воздухе или в воде.
So in fact, the remote cutting can be done either on the air or under the water.
В зависимости от радиоактивности конструкции.
That depends on the radioactivity of the construction.
Решение осуществлять резку под водой либо на воздухе.
The decision is made either we should do it in water or in the air.
Резки на воздухе представлены вот на слайде.
The proposals for the different air methods are represented on this slide.
Потенциально ленточные дисковые пилы.
So for the pressure vessels, the different saws types are represented: the circular one and the bend one. Ну, пилы. Ленточная, да, и вот круглая, да.
Кислородная резка.
So oxygen cutting is also proposed.
Популярность набирает лазерная резка.
And the laser cutting is also getting more and more popular.
Конструкции, стенки больше 300 мм.
So we already can cut the walls of 300 millimeters of thickness. То есть мы это лазером можем делать, да?
Да.
By means of laser.
Из опыта применения ленточных пил для дистанционной фрагментации можно сделать следующие выводы.
This next conclusion may be done through the experience of band saw cutting.
Достоинство метода может быть.
The advantages of the method is
Безопасность.
the high safety. So it doesn't produce aerosols. The high reliability of the equipment.
Как на воздухе, так и под водой.
It can be used both underwater and in the air. The drawbacks.
Оборудование самого.
The high cost of the equipment.
Необходимость частой замены режущего инструмента.
The necessity to exchange the cutting instrument frequently.
Для простой геометрии обрабатывания.
And it is used for the simple geometry of the object. The complicated constructions are not very nicely operated by this type of cutting. As for the oxygen cutting, we can say the following. The top advantage of the method is the high velocity of the process.
И отсутствует ограничение по толщине разрезаемого металла.
And in practical terms, there are no limitation in the thickness of the material. And the fundraising for the process is very low.
Основным недостатком является образование большого количества аэрозолей.
But the drawback is the formation of high qualities of aerosols in this case.
Ржавеющей стали и металлов.
So the we can't cut the stainless steel and colored metals.
Плазменная.
Plasma cutting, plasma burner.
Дистанционные резки.
For the remote cutting, this is a perfect method. It also has a high velocity of the high speed, cutting speed. Okay, cutting speed is very high.
Ограничения по материалам может резать.
There are no limitations in terms of material. It can cut anything.
Недостатком.
The drawbacks, disadvantages.
Ограничения по толщине разрезаемого металла.
So the thickness plays role here. And strong aerosol production.
Кислородное копье.
So, if I'm not mistaken, oxygen spare. Yeah, так и называется, да? Где оно тут копье? Oxygen core lens. Okay, oxygen core lens.
Это плохой метод для дистанционной резки.
It's a bad method for the remote cutting.
Не обеспечивает нужного качества реза.
It doesn't provide the good quality for cutting. The edge of the cutting is not of the high quality. So it's really difficult to cut horizontally in this case.
Меняться только как вспомогательный метод.
It can be used only as an additional method.
Исходя из проделанных рассуждений,
As per our meditation
выполнение таких работ
and the experience of works of this kind, we can come to the conclusion that
на воздухе лучше использовать механические методы резки.
it is better to use mechanical methods of cutting in the air. Especially we are not hurry.
Предложения по методам резки под водой представлены.
The proposal for cutting methods under the water are represented on this slide.
Вот на этом методе
I would like to stop on this particular method.
являлся безальтернативным
It was non-alternative method in the past.
для дистанционной резки толстостенных конструкций.
Or the for the stainless steel constructions cutting. This is the carbon electrode cutting.
Тестирование подводной механической резки ленточной пилой показало,
The testing of the band saw cutting under the water demonstrated
он надежно работает под водой,
worked reliably under the water.
обеспечивается отличная прозрачность,
The transparency of water is provided absolutely perfectly.
гидрозоли практически не образуются.
There are no production of aerosols in this case.
Недостатками является низкая производительность,
The disadvantages is low performance, first of all.
это плазменная подводная резка.
This is the laser cutting under the water.
Обладает высокой производительностью,
The production is very high.
очень быстро загрязняются фильтры при ее использовании.
The filters are very, very briefly contaminated using this way. So this is the carbon electrode you can see on the picture. After being operated, after being worked. This is a very simple equipment. Here you can see the plate being cut. The disadvantage of this method is so there is no visual control of the process in this case. So we can come to the next conclusion, talking about the underwater cutting. From all the methods we have tested, the most universal method is plasma cutting. Nearly all the inner parts of the reactor can be dismantled by means of the plasma cutting. The exclusion only is the thick walled plates, which we recommend to cut by means of the carbon electrode. But now we can also add to the, laser cutting to this method. Here the cutting methods are listed. These their advantages and disadvantages. Next, we continue. Back to technology. We need to for dismantling works, we need the following. Cutting tools for cutting technological connections or dismantled equipment, or cutting equipment into parts in case of fragmented dismantling. Cross-member, grapples, and lift equipment. Protective containers, gripping manipulators, radiation background sensors, aerosol filters, vacuum cleaners, video sensors and process control sensors, and security itself. So here we can see, so I don't know what is English word for patrobak, I'm sorry. So here is, you can see, in fact, milling machine for cutting of RPV, I suppose this is patrobak nozzle. These are the pots. In fact, you can see, so human beings are present. So the level of water is kept higher than the active parts. So there is no any radiation from the system. So this machine is downloaded to the vessel of the reactor and remotely, the saw is cutting these parts from the vessel of the reactor. Once again, we saw this picture before. So all the technical solutions are done on based on the strategy of the chosen method of cutting. And the strategy of the consequent treatment of the fragments. For the dismantling of the pressure vessel of the reactor, two strategies are possible. The dismantling in fragments on the site and the entire complex dismantling with the consequence placing for the decay storage. I will try to skipping the slides. So this is the pressure vessel of the reactor. This is our reactor in Germany, a so-called MPP node. So we tried to fragmentize the reactor's pressure vessel by means of bend saw. So the parts were placed into the protective container. And all of these were placed for the for the decay storage. Что? This is not the correct presentation. No, I'm sorry, but we are missing the most interesting pictures. You will not see them today. Ну, если вы сможете нам подгрузить, мы им потом скинем в презентацию после того, как школа закончится. Okay, so our dear lecturer promised us that upon the school is over, he will add these interesting pictures to the presentation. And as you know, the presentations will be available on our channel, or, you know, I will send them those to you in WhatsApp. Let me describe you the fragmentation under the water and in the air. These are the sites which were previously used for operating of the equipment. This is the core of the reactor. And these are the facilities around the reactor premises. So this zone is for the dry cutting. This is the dry cutting zone. And here is the wet cutting. So the pressure vessel was cut into pieces in the dry zone. The reactor pressure vessel was cut like this. And the upper part of the protective tubes area. The rest of the reactor was cut into pieces under water. This is actually the composition of the dry cutting zone. And here is the wet cutting zone, wet cutting area, if you wish. So you can see here that under the water we also cut by means of the bend saw. Here is the scheme of the. Еще раз, это макет чего? This is the image of wet cutting area on the basis of the basement of the water pool of the reactor. So here is the turning table is organized. And here on this steel column, the special equipment is installed and it can move from the bottom to the top depending on tasks. So the manipulators are installed on this steel column on the left. And the water pool is equipped with the filters that clean up the water, the contamination. Before the fragmentation, so the image is done when the lines by which the cutting will be proceeded are figured out on the skin. So in fact, the whole area of cutting is subdivided into sectors. So starting the cutting, we already know which fragment will have what kind of shape it will have and how it will be later placed into the protective container. Here is the markings for the basket, for the core basket cutting. So each piece has its own angles in each own's measurements on each side. So the basket is placed into the water pool. So then the horizontal cutting is done. And the bottom of the basket is cut it into pieces on the last stage of the process. Here is the basket, and here you can see how do we plan to cut the basket into pieces. We make 3D models for the container. So 3D models of the container and 3D models of the basket. I believe, may I say, it seems to me that they're playing Tetris, in fact. Ну, как в Tetris играете, да? В 3D, да? And we modify the filling of the container in a way the space in the container is used in the most effective way. This is a very interesting construction. This is an annular vessel. So it is firm before you cut it.
Для того, чтобы сохранить механическую прочность при резке,
to keep the stability of the material,
заполняли бетоном.
it is filled in with concrete,
И затем резали на фрагменты.
and then it's cut into the fragments. Канатная пила, это интересно. Это как называется? Ну, это понятно, saw. Ага, okay. What kind of machine? Rope, of course. Канат — это rope, веревка. Rope, saw machine, okay.
Так, здесь я попытался показать,
Here I tried to demonstrate
сколько места займут конструкции.
what volume will the equipment occupy at different types of construction. Oh, this is huge. This is huge.
Реактора демонтировали и оставили в нем все внутрикорпусные устройства.
If we will just disassemble the reactor and will keep all the pieces inside it, it will occupy 215 cubic meters on storage. But if we fragmentize everything, it is twice as big. But in my understanding, this is a huge volume, because I know what is the volume of sea container, of the huge sea container. It's unbelievable. How much is this? In the United States, they keep the reactor like this, so they do not cut it into the pieces. But in Europe, usually they do like this. Our conception is the same. And may I ask you, могу я спросить вас, почему?
Каждый контейнер, он соответствует критериям приемлемости и обеспечивает безопасность.
Okay, I just ask why do Europe and my country sticks to the lower person when apparently it occupies much bigger space? Because of the safety standards, in fact.
И это позиция регулятора.
And this is the regulator's position.
Здесь вот показан защитный экран.
Here is the protective screen. On the protective screen can be placed on top of the reactor pressure vessel. So its thickness is evaluated, it is calculated depending on the activity of the reactor. These are several photos to demonstrate how the dismantling is done. Here is the protective screen. Here is the protective screen, and the reactor is placed inside it. Then the inside tools are placed into it. And they fix it by the lid. This is a standard container for transporting of the inside the vessel equipment, inside the reacting equipment. Here is the pressure vessel of the reactor being prepared to the storage. Oh, God. Impressive, isn't it? This is a part of the vessel filled in with concrete. Here we can see the spots of cutting. How do we call the outer surface? Probably that's everything. If you have any questions, please ask. No questions? Okay. Thank you very much.
Mhm. Mhm. Okay, let's start the last lecture for today. So first of all, I would like to thank for invitation and for opportunity to share with you our experience in strategic planning in radioactive waste management. So a few words about me. My name is Damir Ilyasov, and I represent the joint stock company 12, the fuel company of Rosatom. And my key goal in company is to create radioactive waste management strategy and to control its implementation in our 9 affiliated enterprises. These enterprises such as uranium conversion plants and uranium enrichment plants and so on. So my lecture will be divided in 3 parts. In the first one, I will describe how do we use a digital approach in radioactive waste volume calculation generated after decommissioning processes. A few words I will say about long-term safety assessment and how do we use our digital tools for this assessment. And finally, I will mention information about using of digital tools for radioactive waste management strategy in joint stock company. In joint stock company 12. Okay. So the very big difficulty for us now it's a huge volume of nuclear legacy. We accumulated about 400 nuclear and radiation hazardous facilities that are shut down in Russian nuclear enterprises. And we have a big problem when we plan decommissioning processes. So the difference between plan in fact in decommissioning costs can reach up to 100%. And this is a very big problem for project management. And the key reason of such uncertainty is because more than 50% of decommissioning costs is connected with radioactive waste management, and we can estimate the volume of radioactive waste management after decommissioning processes in the pre-design stage. That's why we try to implement some digital solutions in process of decommissioning planning. And it helps to, first of all, it helps to improve the quality of initial data for decommissioning planning. Here is a conceptual scheme of how do we use building information modeling. So we use 3D modeling of a building. And on the basis of this 3D modeling, we are trying to estimate the volume of radioactive waste generated after decommissioning processes. Building information modeling, shortly BIM, helps us to solve 2 key tasks. First one is a safety assessment for decommissioning processes. And the second one is cost estimation, including forecasting radioactive waste volume. And finally, using safety assessment model and decommissioning cost estimation model, we can create the design of decommissioning of nuclear facility and to justify the decisions that we put in our decommissioning design. Okay, I would like to share some information about what types of final state of a site we are considering in Russia. Here is two options of final state of site and volume, radioactive waste volume. It depends on what final state for decommissioning we chose. And the difference between these two scenarios is what we do with generated industrial waste and radioactive waste. So we have several radioactive waste categories depending on activity of radioactive waste. So the first one is industrial waste. It's a clean waste generated after decommissioning processes. Yeah, we have radioactive waste divided on very low level, intermediate level, high level, depending on activity. And also we have some special category of waste. We call them waste containing radionuclides. And this waste, we have some restriction to dispose of this waste, but these types of waste still not radioactive. So in all our scenarios, of course, low level, intermediate level, and high level waste, we transfer offsite and transfer it to disposal. But the category of waste containing radionuclides, we have some opportunities in decommissioning planning. For example, in a greenfield site concept, we have to transport and transfer it offsite. But for example, in brownfield site, our legislation allows us to put in inside. For example, for backfilling in pits formed after decommissioning. Yeah, and brownfield site for economical reasons and for safety reasons, we prefer brownfield site for the most of our nuclear facilities. Here is some examples when we use on-site disposal concepts, and when we disposal on-site some very low-level radioactive waste, but we have to prove the safety for our regulators that it is really safe for people, safe for personnel working in decommissioning project. Okay, let's move on to BIM development. As I said before, creating BIM model of nuclear facility is the best way to predict, to calculate radioactive waste volume. And we have several stages in this process. First of all, we do laser scanning and analyze some technical documentation about building that we are going to decommission. After that, we form some 3D model, and we cross-link the laser clouds and to create some 3D model with walls, roofs, floor, with technical equipment, with ventilation equipment, and so on. And finally, we make some radiation survey, yeah, and we get points of pollution and put it in 3D model, and we create such as scheme of pollution in each floor of our 3D model. And using this information, we can predict the volume of radioactive waste that will be generated after decommissioning. And we can even categorize by activities, by materials, and so on. And finally, we get a BIM model containing information about all weight, size, perimeters, and material of constructions of elements. For example, we can predict that we have about 15,000 steel after we will dismantle technological equipment. We will have about 2,000 cubic meters of bricks after we dismantle walls, and so on. And using the information, using pollution map, we can categorize this waste depending on activities. Yeah, and also we determine the technological scheme, how we will process the radioactive waste and the other waste. Okay, let's the BIM model allows us to, on the next step, to calculate the decommissioning and radioactive waste management costs. And let's move on to decommissioning cost estimation methodology. First of all, we need to upload all information from BIM model and to create some work breakdown structure on the basis of data set from BIM. And estimate, first of all, we estimate the cost of decontaminating of floors, walls, and equipment, and the cost of dismantling. After that, we can forecast the volume of radioactive waste categorized by activities, materials, using the surface contamination information from BIM. After that, we develop the strategy for radioactive waste. For each types of waste, we determine technological chains and determine infrastructure that we need to create for radioactive waste management. And finally, we provide uncertainty and sensitivity analysis. This is a big statistical analysis that allow us to calculate interval values for costs and provide some statistical analysis of costs that were calculated. So here is the interface of special software that we created for decommissioning planning. It is decommissioning planning application. This application upload all information from BIM model, calculate costs of dismantling. We use some unit prices for each type of work, and on the basis of work structure, we estimate the cost of dismantling, decontaminating, radioactive waste management, and all stages of radioactive waste management, such as packaging, transportation, transfer to disposal, processing. Also, we estimate the structure of costs is salary for employees. This is material expenses and so on. And finally, here's some example of our calculation for uranium plant. This is uranium conversion plant, and we can compare. Okay, on the basis of 3D modeling and using decommissioning planning application, we estimate that if we are going to reach green side final state, the costs will almost 2 times higher than, for example, we would choose brownfield site. And that's why brownfield site is much more interesting for us, because it's on the basis of economical feasibility analysis and so on. And as you can see, this is pretty clean site because radioactive waste management is less than 1% of all generated waste. Okay, let's move on to long-term safety assessment approach. As I said before, on the basis of 3D modeling and on the basis of some mathematical codes, mathematical applications, we can also estimate 2 parameters. The first one is atmosphere transport of radioactive dust generated during decommissioning processes. And according to our national legislation, we have to prove that the technologies chosen for decommissioning allows us not exceed 10 microsieverts of annual radiation dose for population during all decontamination and dismantling processes. And this is very crucial estimates in Russia, because a lot of nuclear facilities are located in huge cities like Moscow and St. Petersburg. And that's why we have to do our work safely. And we use 2 created in Russia applications for this task. The first one is Logos Aerohydro, created by Scientific Research Institute of Rosatom. And the second one is called Veltran, developed by Russian Academy of Science. Also, when we consider on-site disposal strategy, as I said before, we have to prove the safety of this decision. And we create a 3D migration model for radionuclides in soil and in groundwaters. And here is some example how here is some prediction for the 10,000 years. 10,000 years of migration radionuclides in soil. And we use some special underground maps. For these tasks were created also two numerical codes in Russia. The first one is Logos Hydrogeology, also created by Nuclear Institute of Rosatom. And the second one is called Gera, developed by Russian Academy of Science. Okay. Okay, next, I would like to mention some information about some digital tools that we used for our divisional decommissioning strategy and our divisional radioactive waste management strategy. Radioactive waste management strategy is a multi-component task. It must be carried out in accordance to national legislation. And for example, in Russia, according to practical experience, the national legislation regularly improved. And operating organizations also share with their practice with Rosatom, with our national regulators, and provides significant assistance to improving the national legislation. This is really very important issue because it is really difficult to create the perfect regulatory and legal frameworks. For example, about 2 years ago, our waste classification criteria was changed. And also our national operators of disposal facilities also analyze the acceptability criteria for disposal and also improve this part of legislation. So what do we need to plan in our divisional strategy? Of course, we need to plan the methods for processing radioactive waste generated on our plants. We have to bring waste to acceptable criteria for disposal. We have to choose containers. We have to create infrastructure. And for planning, of course, we have to accumulate data about volumes of waste generated within fuel company enterprises and so on. And finally, we have to analyze the location of disposal storage in Russia, because in Russia we create several disposal storage. Nowadays, it's constructing 2 disposals in Ozyorsk and Seversk. And if you still not have your national disposal for radioactive waste, it is very important to analyze the location where this disposal facility should be constructed. And of course, all these multi-component tasks can't be solved without digital methods, and we have been creating for last several years such digital tool. Okay, here is some levels of developing of support and automatization of system of planning for radioactive waste activities. The first level is all data in enterprises is collected in tabular form from sites to management company. Manually, personnel in joint stock company consolidate these tabular forms in one form, and we analyze overall tabular form, and decision making process are based on these manually consolidated form. And the second one, we create a special application to automate the process of collecting data. So in each enterprise, the consolidation of data in the database happens automatically, and the data is analyzed by decision makers, and the final decision for strategy of radioactive waste management in our division is made by a person. The third level of automatization is automatization of decision-making processes. The database are analyzed by special computer codes and generate some optimized decision. And these decisions are analyzed by decision makers. And on the basis of this information, we create radioactive waste management strategy in fuel company. And the last one, automatization, is when the entire infrastructure is equipped with sensors that automatically transmit all information about radioactive waste to database. The data is consolidated automatically. The special computer codes analyze this information and generate the optimized solution for decision maker. And nowadays, we are trying to design our radioactive waste management infrastructure with special sensors that also allows to make some predictive analysis and give some and warn you if there is some troubles with your infrastructure for processing radioactive waste and so on. And nowadays, as I said, currently we are at level 2, but we try to get level 4. And now we develop special digital tools for radioactive waste management, and the goal of this model is to accumulate all information about radioactive waste in a fuel company, and we try to model all processes of radioactive waste management, and we do operational planning based on systematized information. And here is some tasks for our digital tools that we can also solve. We organize unified information space about radioactive waste, about designers, about types of containers that we can use to that we can use for conditioning of radioactive waste. Also, we make some automatization of routine processes as an enterprise because we automatically prepare some standardized form that we have to share with Rosatom and our national regulator. Also, on the basis of this tool, we can control and monitor all processes connected with radioactive waste. For example, we can compare the volume of radioactive waste generated in fuel company enterprises and how many wastes were transferred to disposal. And here is some conceptual scheme of this digital tool. So digital tools consist of databases, radioactive waste sources and formation forecast, all technological and installation equipment, conditioning waste packaging. We have all transportation methods. So we can transport radioactive waste using, for example, railway or maybe another transport. This database includes financial economical parameters, some physical and chemical reference books, and so on. So we also implement in our digital tool a lot of mathematical models, so we can forecast all processes with our waste. So modeling all processes like radioactive waste storage, processing, conditioning, and so on. Finally, when we want to create some scenario or strategy, for example, I want to analyze information about construction and new waste processing facilities, and I put in this mathematical model the parameters of creating nuclear facility. And this model allows me to analyze the cost of building these facilities and the potential benefits after I create this facility. And the system generates our investment documents for fuel company. Okay, this simulation model allows testing a lot of parameter changes in our radioactive waste management system. For example, we can ask on some questions like when do we need to get radioactive waste accumulated in our storages? How and where to process radioactive waste, what infrastructure and equipment to use. Maybe I should use existed infrastructure, or maybe I should create new one. I can analyze the different type of packaging. I can analyze what is the best way to transfer radioactive waste to disposal facility, and so on. Here is a huge volume of mathematical models that we implement in our specialized software. And probably right now I will show you some video, but I would like to apologize because the interface of our digital tool are not translated in English, but I suppose that the video will be informative for you.
Radioactive waste management is a complicated process that requires careful planning and prediction. Radioactive waste management is a solution that takes the management of radioactive waste to a new level of efficiency. The system helps in solving key tasks from strategic planning to operational management. It is a tool that combines data, ensures transparency of processes, and improves forecasting accuracy, which allows you to optimize costs and minimize risks. All information for data analysis and decision-making is collected in one place. The system combines data on technologies, equipment, packages, logistics, and waste disposal sites in a single information space. The system accumulates and organizes data, allowing you to visualize objects and routes on interactive maps. Everything you need to know about radioactive waste is in one tool. The model collects data on radioactive waste, including mass and size and radiation characteristics, and classifies them by sources of education. It builds production and technological chains in the form of an oriented graph, allowing to optimize each stage. The system allows you to simulate various scenarios and evaluate the effectiveness of production processes, taking into account possible factors. Financial and economic indicators are calculated for each scenario. Our system is a tool for accurate feasibility studies. It is planned to provide for monitoring the implementation of the plan at all levels, from individual operations to strategic goals. A fact-based plan analysis will provide up-to-date information on the completion of tasks and help you make management decisions quickly. We are actively working to improve this system. Our plans include the introduction of intelligent search, integration of 3D models, and the ability to create customized reports tailored to the specific needs of the customer. We strive to create a solution that meets the requirements of the Russian nuclear industry and the BRICS market. Simulation model radioactive waste management system innovations in waste management.
Okay, here is some technical difficulties in creating these digital tools. Rosatom has requirement to use only import-independent digital technologies and high standards for information security, because there are a lot of information about radioactive waste volume generated in fuel company. That's why we have to be ensured that all information stay within fuel company. And the development of such digital tools involves a broad spectrum of specialists from various scientific spheres, such as physics, technologies, and economists, and so on. And we have to create a really large number of mathematical models and to create our own methodology for generating radioactive waste strategy in fuel company. Okay, I would like to end. If you have any questions, please. Yeah. No, this is nowadays this program I used only in fuel company, and of course it's we think about selling this program for our customers. Demo version of this program, I suppose we will create it soon. If there will be demand, we will create, of course, demo version. Okay, okay, we will discuss. Okay, thank you. Have a nice evening.